to the next day of SLE and the first session of the day. Thank you very much for showing up. I hope that you have enjoyed the banquet yesterday. My name is Vadim. I will be chairing the session, and we have 3 presentations planned ahead of you. Remember that we are streaming, so when you are asking questions, there will be a microphone in the middle of the room, so queue for that and ask your questions there instead of shouting. If you cannot move, then I know, give me a signal and I'll go to you with a microphone. All right, the first speaker is Kyprian Theodorov, and he will talk about temporal breakpoints for multiverse debugging. The floor is yours.
Thank you, Vadim. So, yeah, I guess I'll get to the next slide to speak about the motivation. So, in our context, we are thinking a lot about formal specification. Is the formal specification aligned with the middle model with the user? And knowing that these formal specifications are wildly non-deterministic, and basically we want something that in the early design phases aids the user to interact, the designer to interact with the partial specification in order to increase confidence either in the specification itself or in the properties that it needs to verify. And in the later design phases, if a property is violated, we'll like to have some interactive debugging to be able to do some differential diagnosis. On the other side, we have concurrent programming. And the idea is where do we get this set of behavior, this non-determinism? The problem is simple. If we have schedule-sensitive bugs, we'll have to somehow use the scheduler during, to remove the scheduler during the debugger, or to generalize it in order to understand where that bugs come from, and that brings in non-determinism. But then, if we are doing that, linear breakpoint in classical interactive debugging becomes a graph reachability problem. So basically, it gets this algorithm from the formal specification side. And that was proposed as a multiverse debugger in 2019 at ECAP. But then, this reachability analysis, if we have huge problems, we'll have a scalability problem. So in order to manage the scalability, we'll need to somehow do abstraction, either under approximations or over approximations, which increase even more the non-determinism and brings us closer from the programming world to the formal specification world. So in 2022, we proposed to reductions in models that brings, again, this under approximation ideas from the formal side towards towards the interactive debugger. And since we are now speaking about sets of behavior instead of one linear behavior, we know from the formal methods side that temporal logic allows reasoning on sets of behavior. So the idea is, how can we get this temporal logic to interactive debugging that now has to reason about sets of behavior? So our purpose is to leverage this interactive debugging in order to ease the life of formal specification engineers. I have some questions for you to ponder during my talk. Does your favorite debugger support temporal logic breakpoints? Does your favorite modeling tool have a debugger? If it does the debugger support these temporal logic breakpoints? If not, start using a better modeling tool. And I think this is maybe more like a call for the community to start thinking about these problems and start helping ourselves and our colleagues that are in the industry. And by the way, there is one tool that I know of that is doing this. It's Simulink. In their temporal assessment tool, they have this signal temporal logic that it's somehow implemented there, and apparently it's used successfully. So with this temporal logic idea, we'll have to reclassify a bit our breakpoints. So we have identified 4 types of breakpoints. We have configuration breakpoints. Basically, in this case, it suffices to look at each configuration during a run, the memory configuration of our system, in order to understand if some predicates are true or false. We have step-based breakpoints. which are evaluated on two link configurations by an action. So in that case, we have like memory breakpoints where we can break if a variable change. We have difference breakpoints, the rising age of a Boolean variable, the falling age of the variable, or activation breakpoints, basically the function X got activated or the action is triggered. And we'll have history-based breakpoints, where the breakpoint conditions evaluated by integrating some variable over the history of the execution and then checking that variable for a value. So there maybe we have a breakpoint that will say, let's take the sum of A, and if that sum becomes greater than 2, then break. Or I want to break on the third occurrence of the function f. So do you see this counter getting there and getting incremented as we progress during the execution? And the last breakpoint, and maybe the most extreme, it's coming from temporal logic, where instead of having this look in the past, as we had with the history-based breakpoint, we start looking to the future in order to start to understand if there are some infinite behavior that will prevent useful work. And basically that will help us isolate some cyclic behavior where something that we want to happen doesn't occur. And basically we can say something like A equal to 5 is inevitable. So that will mean that if ever we find a behavior that where a cyclic behavior where A is not equal to 5, then we have a problem, because if the system, the scheduler, will get us in that loop, we might get stuck, become stuck there forever. Another, it's eventually forever B becomes false. So basically at some point in the future, B becomes false, for instance here. And then it needs to stay false forever. But here we see we have this loop where B becomes true again. So that invariant is not true. So let's take a step back and think a bit of how can we build these tools that survive and that we can reuse them. So there are a bunch of approaches, and I show you here 3 of them. The first one is like take a language, like MATLAB Simulink, as I was saying earlier. It supports this temporal assessment, and let's do transformation towards that language, and then use that debugger. But then we have this impedance mismatching between our initial formalism and the formalism of our debugger. Another approach, which is common in this community, is to have some meta-language tooling that will help us generate the tools for testing, for coverage, for debugging. And but we are in the last, this old school category, let's say, which is more oriented on API and like say, okay, we have this black box hypothesis. I don't want to care about either the meta-modeling language or the way the people are implementing their semantics, as long as I can write some glue code that will expose some API that's somehow common, confluent between a set of tools. And that enables us to explore this space from a tool perspective with exploring basically families of tools. And today, the family that we're exploring is debugging, and more specifically, multiverse debugging. So in multiverse debugging, we have a bunch of stakeholders that will provide us with a specification, and they will want to ask some questions about the specifications, and in our case, those will be multiverse breakpoints that are breakpoints on these sets of behaviors. And our stakeholders will interact with the semantics of the debugger through debug actions, and they will observe projections of the debug configuration that will tell them, yeah, you are here in the multiverse, and you can go there, and that way. So in order to make this modular, we'll have to have an API here that it's implemented by our specification language that's designed by any subject language provider. And the other side, in terms of the breakpoint language, if we want to open the box and allow different logics to be used for the breakpoint language will have a similar API. However, we should note that the breakpoint language, it's dependent on the execution of the specification language, on the semantics of the specification language. So that's a small point. So what is this interface? It's rather intuitive. We have some generic types. The configuration type is like the memory dump of the semantics. And then we have some set of initial states, the actions that we can execute from one state, and an execution function that basically, given an action and a memory state, it will give us a set of target configurations. And this is an approach similar to the temporal logic of actions of Lamport and omnisemantics that got presented this year at TOPLAS. And in order to be able to ask questions over the semantics, we'll have this evaluation function that will evaluate a given expression over a computational step, and it will give us some value. To do the under approximation, we had proposed to use a reduction function that will map any configuration towards an abstract value, alpha, and a bunch of projections that will show the user the state of the debugger and the actions that he can take. So from this perspective, what is a multiverse debugger? Basically, it's this dependent semantics. We need a subject language semantics here that has a step action. So basically, if I'm somewhere in the execution, I might want to step to the configuration 4 or to the configuration 5. I have to be able to jump back in the past to allow this time-traveling semantics like in omniscient debugging. We have the need to have a select configuration because from one configuration, while running an action, if our language is non-deterministic, we might get multiple target configurations, so we have the select action, and finally the run to breakpoint action, which basically will have to do this reachability-like analysis or over the state space. So in this approach, the multiverse debugging semantic is independent from the subject language, and it's built through composition of these smaller operators, the blue operators and the algorithms and everything. So the scalability comes from this reduction part, and we have connected it in the past to the AnimUML semantics. So now today, the story becomes a bit integrated because we have to replace this run to a breakpoint implementation, which was limited for configuration-based breakpoints, and to get to these temporal breakpoints. And how do we do that? It's a lot similar to model checking, with the big difference that we'll have to replace the initial state of the original semantic from which typically we start the model checking, and then we'll have, so basically in ongoing debugging semantics, we'll start somewhere, we'll do some exploration, maybe get to 5, we'll go back, we'll go to 3, and then we get to 7. And at this point, we want to start the run to breakpoint operation, and basically we feed it in a finder function that will replace the initial configurations of the subject language. Then we get the breakpoint, which will be represented for simplicity as an automata here. We get the breakpoint with its semantics, and we do a synchronous composition in between the subject language and the breakpoint language semantics. But basically, this is a lazy synchronous composition, and yeah, that basically helps us to get the breakpoint to filter the execution and in order to focus on the parts that we're interested in. And then, as is typical for model checking, the subject language will consider that the subject language semantics has all its states as an accepting state, and then basically the intersection will consider only the states where the breakpoint automata has accepting states. Okay, so we compute this, lazily compute this, we have this specification that will allow us to compute at runtime the synchronization. And then we have to do like a lowering path that will transform our rich semantics in like a more graph-like structure. That's again done lazily, and an emptiness checker algorithm, which is standard algorithm from the literature. So basically, in our example, we'll start from 7, and we'll start exploring. We'll get to 8b, and we can stop because we found an accepting state. When we have found an accepting state, what do we have to do? We have to compute the witness trace, as is typical again in the model checking community, and patch our history from the 7 that we had, where we have started, with the witness trace that we have found. And then show that to the basically the state of the omniscient debugger semantic changes. So the AnimML tool presented in 2020 at Models basically allows us to do some state chart modeling with class modeling and everything. And the idea since the beginning was to allow us to do execution of partial models. So last year we have implemented the reduced multiverse debugger inside. So we have this branching history that allows us to walk in time on different universes and yeah, to write these reduction functions and everything. And today we have integrated again AnimML with this more generic approach where the breakpoint language, where the breakpoint condition becomes a language itself, actually. And basically we have this debugger core, the finder function that we have seen, and the dependent semantics that will have to fill in somehow. So we took the previous implementation of this AnimML subject language. We had to re-implement the evaluate step function because it wasn't there, because previously we were supporting only conditional breakpoint on the configuration. And then we implemented a bunch of different languages with different semantics for the breakpoint language. So we have a simple regular expression language. We have a breakpoint language which uses AnimML state chart themselves as a breakpoint language. So we have the specification as an AnimML state chart, and then we can specify the small state charts that are dependent on the subject state chart. And we can do history-based breakpoints with them, and step-based breakpoints, and configuration breakpoints. For the liveness breakpoints, we have to use a different emptiness checker because our automata that we need to use for that becomes like a Bushy automata, and in order to find these cycles in the execution. So basically we were able to reuse some tool that we have developed some years ago that are transforming LTL to state chart-based Bushy automata, and again, reuse the semantics that we have enriched here of AnimML in order to be able to do that. So, yeah, so these are temporal breakpoints which increase the conditional breakpoint expressivity. We propose formal methods, taxonomy inspired by the literature, where we can speak about the state, the execution step. We have a look in the past through the safety properties, in the future through the liveness properties. Basically, this approach enhances the genericity of the language agnostic multiverse debugging that we already proposed last year. Everything is formalized in Lean. It was illustrated to the integration of in the AnimML environment, and you can have the code here. We have 3 different breakpoint languages, as I just told you. And basically, we had a paper at Modeva 2023 where we tried to use it to debug Paxos and have this iterative approach to building a Paxo consensus algorithm. So tomorrow it will be relatively easy, we believe, to do some user study that will try to understand what are the needs, what are the opportunities of temporal debugging in the context of complex specification. And it will be really nice to go from the command line interface that we have today as an implementation to a nice graphical user interface with some real user experience help magic. Yeah, not so easy. It will be to find a trade-off in between the intuitiveness of the logic that we are using for expressing breakpoints and its expressive power, and that's typical in the formal methods community, and it has a huge history, and we are oscillating in between all these things, and yeah, that should be solved somehow one day, maybe. We should be hopeful. And we see some difficulties that might arise if we are having heterogeneous specs where you have these multiple languages. Then the composition should work, the approach that we're presenting should work, but there might be some details that need to be solved if we're having some, let's say, mixed signal or abstractions that are mixed at different levels in our specifications. So thank you very much. I forgot to mention at the beginning, this work was done mainly by Mathias Pasquier and in collaboration with between Insta Bretagne, Ezeo Angers, and Lucio. And yeah, what do you think? I have a bunch of questions for you also. So thank you very much.
We have time for questions, so please come up here.
So thank you very much for your interesting presentation and work. I wonder whether, to which extent the breakpoint part of your system requires the jump operation that's part of the interface, because that seems quite a tough ask on language implementations.
The jump operation is just an operation that it's useful for multiverse debugging. But actually, the run to breakpoint doesn't require it. The operation, the four operations that I'm presenting here are somehow independent. But at the same time, that's at the multiverse debugger semantic level. However, when we are implementing a reachability like query over the partial state space, in this case, starting from the node 5 there, in order to get to everywhere, yeah, then you have to have some storage requirements, and basically you get typical issues that you have in a model checking context. That's why we have thought about under approximations and yeah. But with the jump, it's not required. If we don't store the history, we are not able to go back in the past, and that will be fine. It will be like more like a typical debugger, and we'll still can implement this run to breakpoint.
Okay, that's very clear. Have you considered any other case studies, or are you aware of languages that you would be able to apply your implementation to directly?
Actually, the first prototypical implementation that we did was on TLA Plus in like 2016 or something, where we had some of these ideas already working a bit. This is a lot nicer presentation than our prototypical implementation that we did back then. And I think now the formal specification community starts to understand a bit the interest behind debugging. And TLA Plus has a Visual Studio Code extension that implements more like software debugging. It doesn't get this sophisticated, but it's a good step towards that. I think VDM community have something around it. B method has something around it. And on the software side, the initial paper was motivated by the debugging in actor formalism. Like I don't know what was the name of the actor formalism studied, but yeah, I don't know the real implementation on the software side. that's used. Besides, of course, MATLAB Simulink with their temporal assessment.
Still have time for questions? All right, I'll go with one of mine. So in your case, you see basically a breakpoint as an automaton.
At the end of the day, it will become that, yeah.
Yes.
It's the semantic of the breakpoint will be the semantic of the language, which we see it from an operational perspective as a state transition system. So
Yeah.
an automata.
Yeah, but
It's not really
later, in order to merge it with the configuration automaton and so forth, you really need the automata power, right?
Yeah.
So automata have a very nice hierarchy. So where do we need to be in that hierarchy, and what are we missing by staying at non-deterministic finite automata, which is, as I understood, if I understood correctly, the current state? But you did mention that at some point when you go further, you need a Buggy automata.
Yeah. So basically, non-deterministic finite automata from the actually, I think on that side we might get to maybe get to push down automata and a lot more expressive logics on the breakpoint side, but will probably be limited at this look on the past. In order to be able to look and identify infinite behaviors that don't that preclude useful work, then we have to go to these cycle detection techniques and fixed point computations, where we get to these more sophisticated approaches like Bushi automata, Rabin automata, mu calculus, where we have this power of computing complex fixed point over the state space of the subject of interest, you know. So it will be interesting to see where can we get, and I think this maybe one of the things where I'm rather proud of this approach that we have here is that it puts the question on the table, and it somehow bridges the gap in between these model checking guys that are very sophisticated and mathematically friendly, and like programming community where, yeah, we have semantics, and we can implement them. We can implement this interface. We did it for BPMN, for UML. We did it for TLA+. We did it for a bunch of SDL, for a bunch of formalisms. So the semantics are there. They are implemented. And now let's bridge the gap and like have simple tools like a debugger, allow us to reason with temporal logic, and this way maybe the designers will get some feedback before verification part, where you have this huge temporal logic formula, this huge specification, it doesn't work, and you start scratching your head, and you are basically, yeah.
Okay, thank you very much. Let's thank the speaker once again. And can the second one, please?
Hopefully somebody remote with some headphones on didn't get a brain freeze.
That's my mail. That's me. Just closed it. there is nothing else there. Come on. This mirroring, wait a second. Okay.
Thank you very much. So this is Bram from the Free University of Brussels, and he will talk about cross-level debugging for static analyzers.
Okay, thank you. So let me first start with talking a little bit about static analysis itself and why is it so difficult to develop debugging tools for. So some terminology, what does a static analysis do? Well, it takes some source code as an input, which we will call the analysis target. Then some analysis implementation will run some static analysis on this input, and in the end, we will get an analysis result. Now, as a concrete example, you could consider a very simple type analysis. So let's say that as an input, we get a program that computes the factorial of some number, and we run a type analysis on this program. We will get, hopefully, some kind of integer number as a type in the end. So this is what our analysis could predict. Now, usually, what do we want of a static analysis? Or at least want of a static analysis that are, well, we want two properties, which is termination and soundness. And so what does termination say? Well, for any input program, we would like to terminate the analysis. So even though the input program does not terminate, our analysis implementation should terminate on that input program. Next is soundness. What we want is that the analysis kind of over-approximates the behavior of the program. It considers all possible execution states that the program could have when we give it to a concrete interpreter. Now, of course, it's very well possible that an analysis developer is not able to satisfy these properties because there are some bugs in the analysis implementation. And then, yeah, we could get a violation of the termination property, or we could lose our soundness. Usually, we see this reflected in the analysis result. Certainly for soundness, suddenly we might get a value that does not correspond to the expectations that we have about the input program. For example, a program that computes the factorial, it would be very strange if our static analysis would derive that the output of that program is a string instead of an integer. Then we would call that program or that static analysis unsound. So that is the kind of stuff that we can have for bugs in a static analysis. What do traditional debuggers do? Well, they would target the analysis code or what we call the analysis implementation, but that is actually quite difficult because what we have is two code bases. We have the inputs that we are analyzing at the moment, and we also have the analysis implementation itself. And usually what we see is that if we give the analysis a specific input, then we see some bug, but with other inputs we might not see the bug. So in essence, we want to reason simultaneously about the analysis target and the analysis implementation. Furthermore, it is not entirely clear where we would put things like breakpoints in our analysis implementation. Because the analysis implementation, it's quite large. We have an implementation that is a few thousand lines long. And so it's not clear where we would have this breakpoint to see our bug reproduced. On the other hand, when we look at a specific input program, like our factorial, perhaps we have a function string to number, which does not function properly or which doesn't have a good analysis implementation. And maybe it would be more interesting for a programmer that is developing our analysis implementation to put a breakpoint in the inputs of our analysis implementation rather than in the analysis implementation itself. And so in related work, static analysis developers were consulted to see what their difficulties were while developing static analyses. And so there, the same debugging target mismatch was found, that we have these two code bases, the analysis target and the analysis implementation. And well, yeah, it's not very easy to reason about those simultaneously. And furthermore, the survey found that the generic visualizations and state inspectations of debuggers are not adequate enough to debug static analyses, because the states of static analyses, they become quite difficult and very difficult to reason about, certainly if you can just only see the memory structures that we have in the analysis implementation. Rather, developers would like to have analysis-specific visualizations, like a control flow graph, so that they can see what the analysis is doing in terms of its current state. And so this is an idea that was put forward by these authors. However, one limitation of their work was that they didn't really consider the use of breakpoints. There is some suspension available, but you cannot really express conditions that you would need for breakpoints to be executed in the sense of conditional breakpoints, and I will explain in the next few slides why this is a problem for static analyses. To do this, I would like to give some background on how we perform our static analyses. So again, our factorial program, what does it do? Well, yeah, it computes the factorial, and for number 5 we get, when we execute this in a concrete interpreter, we get the value 120. However, this program does not always terminate for all inputs. For example, if we give it -1, our end condition is never reached. And so if we would just, as a static analysis, use a concrete interpreter, well, then our static analysis would not terminate. And to solve this issue, we usually go for abstract interpretation rather than concrete interpretation. And in this style of static analysis, we replace the concrete values that we have in our program with abstract values, such as types, and then run the program with that kind of values. And usually, we represent those things using mathematical lattices. For example, here on this slide, we have a lattice that represents a type domain. On the bottom, we have no information. Then we say that it's precisely an integer, boolean, of string, or any combination when we go up in the lattice. And so the goal of this structure is to make the state space of our abstract interpreter finite, so that our abstract interpreter always terminates on all inputs. However, this is also some kind of source of bugs, because we have to re-implement all primitive operations on these abstract values, such as multiplication, addition, and so on. So to show you how this works, let's go back to the implementation or the analysis of our factorial program. The end result would be int, as we would expect, and we arrive at this by replacing all concrete values with abstract values, such as the 5 that we replace with int. And the execution of the program continues. So we see that the variable x is also replaced in the condition of the if expression, and then also in the multiplication that we have in the false branch of the if expression. But this also shows our second challenge that we have in debugging static analyses. That is that our program execution becomes non-deterministic. And so what a static analysis would typically do when it does not have enough information to determine, for example, for an if expression, whether to execute a true or false branch, it would execute or explore both. A second ingredient of our static analysis is the modular static analysis. And so in this approach, instead of analyzing the program as a whole thing, we split the program into multiple parts. So for example, here, we consider the main function as a part or component of the application. Then we consider the decrement1 function as a component, factorial function, and that's it. And so the idea is that in that analysis, we could analyze those independently and then combine the results of them together. However, this is not always very trivial, because components are not really independent. They can call each other, for example. We have here main calls factorial, and factorial calls decrement1. And furthermore, they also share variables with each other. And when those are updated, we might also need to reanalyze one of the components that we thought were independent. To illustrate this, I have a very small example. So what you see on the right now is what we call a store, which is an abstraction of the program's memory. And at the moment, we don't have any information about the variables in this program, so everything is bottom. Now, let's say that one of the values in the store is updated, for example, in the decrement1 function, then it's normal that we have to reanalyze the factorial function because it reads the return value of the decrement function. And to do this, we keep track of a work list to remember what we have to do next. So then we go to the factorial function, which again has a value where the main function depends on, and then our story continues with a new iteration of the analysis, and we go to main, and then this is where it stops because main doesn't have any values that could flow back to factorial or decrement. This highlights the third challenge of having a debugger for static analyzers, and that is that it might take a while before we actually reach the bug in our static analysis implementation, because we might do many iterations before we get to a value in our store that triggers the bug that we are talking about. So these three challenges highlights the problems that we have, and we propose the following solution. So we propose cross-level history-aware and domain-specific breakpoints, and I will explain each of them next. But first, I would like to introduce our debugger interface, which is inspired by the survey that was done a few years ago. So at the top in area A, you see the code that we are analyzing, the analysis targets. In area B, we see the component graph that I've also introduced on the previous slide. And in area C, we see the visualization of the store. Now let's talk a bit about color coding we have here. So in blue, we have store addresses. And in green, we have the components that I was talking about a few slides back. And then in the store, we also have a specific color coding where we use the green parts for addresses that are just added to the store. And by just added, I mean between the current suspension of the analysis and the previous suspension of the analysis. And then in yellow, I have my updated addresses. So addresses that are changed between the current suspension of the analysis and the previous suspension of the analysis. So then, of course, we also have unconditional breakpoints. We have implemented them here as just conditional breakpoints, but with a true. This hashtag T means true, with a condition that always evaluates to true, so it always breaks. It's an unconditional breakpoint. But of course, this is not very interesting because, as I have specified earlier, we have this problem with our many iterations of our analysis before we reach the problematic part of our application. So we actually want to use a condition there. And for that, we use domain-specific conditional breakpoints. And the breakpoints that we came up with are all related to the state of the analysis. And there are three parts of the state of the analysis which are important to us. The store, that I have explained earlier, the lattice to represent our abstract values, and then the work list to see what components are added to our queue to be analyzed next. And each of these categories have specific breakpoints associated to them. For example, for the store, we could ask the debugger whether the store has changed before the current suspension of the analysis and the previous one. To give an example of this, I have our factorial program again. And here the breakpoint only breaks when the value in our store stored on address x semicolon 4 is an integer. So we have two types of breakpoints here. We have the store breakpoint and the lattice breakpoint. Now notice that this breakpoint is placed in the analyzed code rather than in the analysis implementation. This enables us to use the control flow of the analysis, or of the control flow of the program that we analyze to place particular breakpoints. For example, here, we know that this breakpoint will only be triggered when the factorial function is executed. If we would place this breakpoint in the analysis implementation itself, we would have a much harder time to only break when we reach the factorial function. So this makes the life of the analysis developer much easier. And secondly, even though the breakpoints are placed in the analysis code, it talks about the analysis implementation. Here we refer back to a structure of the analysis itself, mainly the store. So the breakpoints, they are not just conditional breakpoints about the input of our static analysis, but they actually cross the boundary between the input program and the static analysis implementation. Of course, we have more predicates, but you can find a full list of these predicates in the paper. So now briefly, before going to how we validated our debugger, I would like to explain how the conditional breakpoints are evaluated. So basically, we have three parts. We have the debugger itself, we have the static analysis implementation, and then we have what we call a predicate evaluator. And so in the first step, what would happen is that the static analysis notices that the input program contains a break statement. Now, we don't evaluate the expression of the break statement in the static analysis itself. Rather, we pass it to a predicate evaluator. And the reason we do this is because our expressions, they shouldn't really influence the analysis result. Instead, they should only query about the analysis state, but not change it. So that's why we have this third component, the predicate evaluator. And in step 2, the expression is passed to this predicate evaluator, which then maybe one, twice, multiple times queries the static analysis itself about its state, and then decides whether to suspend the analysis or not by signaling true if the analysis should suspend and false if it should not suspend. To evaluate our approach, we implemented our debugger in a framework called MAF, which is the modular analysis framework. And we searched for real-world bugs in the repository of that project. And to do that, we looked for words such as bug or fix to find a particular set of commits. And you can see here that we have 3 commits, actually one more which is not shown on the slide, which fixes particular bugs in the analysis implementation. And then from all these commits, we selected 4 real-world bugs, and we also introduced a synthetic one, which you can find in the paper. And then we reintroduced the bug back into the current version of our framework. Keep in mind that the actual root cause of the bug was not known to the first author, and the first author also had to synthesize programs that would trigger the bug. And so the goal was then for this validation to see how we can use our debugging infrastructure for finding the root cause of the bug. To give an example here, we had a bug that resulted in an analysis that did not terminate. What the program does is not really important, but it just computes the sum of the numbers that were given to the sum function. And what we would expect if we sum 1, 2, 3, and 4 together is that we would get the value 10. However, our analysis does not terminate. And this is because, well, we actually didn't know. We had to find the bug, of course. But probably the reason for this problem was in how we triggered reanalysis of components. So what should happen is that if some value changes in our store, the component that depends on those values is added to the work list, and then it's reanalyzed. However, if nothing changes anymore in the store, the analysis should terminate. So let's see if that's the case in our example program. So at first, what we did is we placed breakpoints on each function of the analysis target to see whether there was a single component that actually resulted in our non-termination issue. And so as you can see in red, we have the line that is currently suspended on. And in the beginning, of course, it goes to the main function, then it goes to the compute function, it goes to the sum function, and then it goes to the aux function. And each time you have seen that in the background of my slides, the store was updated. We had these things highlighted in green, and we have these things highlighted in yellow to see what things changed and were added in the store. Now this becomes actually interesting at this point. The auxiliary function, what it essentially does, it implements a recursive loop over a list. And so this takes quite a while to stabilize. You have all these elements of the list that you have to consider, or 1, 2, 3, and 4. And so it takes a few iterations to reach that point. However, what we notice is that the analysis does not stop when the store has no other values that change. So here we have the store, which has only white lines, which means that no value has changed between the current suspension of the analysis and the previous suspension of the analysis. So this suggests that the bug is indeed in the auxiliary function and has something to do with lists. Now, we have placed breakpoints, and actually unconditional breakpoints on each line in the functions, or on each function in the program. And what we have seen is that this approach is fine to find some indication where the bug could be, but of course, it takes quite a while to reach the actual problem. And what we have seen is that with these unconditional breakpoints, we have to step through the program into the next breakpoint for a total of 16 times. So here is where our conditional breakpoints shine again. So what we noticed is that the analysis does not terminate for the aux function. And we have also seen that the aux function has just a single argument that it depends on. So that's the only cause of our bug, probably. So what we do is we wait until the store has no changes anymore, and then we will break the analysis. And this is expressed in our conditional breakpoint by using the store changed breakpoint together with our L address. And then we invert it so that the analysis only breaks when the store does no longer change. And this results in an analysis or a suspension of only 6 times. Then we ask ourselves, for all of these bugs, how often do we use our conditional breakpoints? And so what we see is that the what we call regular breakpoints on this slide, which are just unconditional cross-level breakpoints, they are often used first to find the bug where it could be, and then the domain-specific breakpoints are used to further limit the region where the bug could be, and also to reduce the number of iterations the analysis has to take before we reach the problematic behavior. In future work, we would like to extend the set of meta-predicates that we have for expressing the conditions in our breakpoints. And then it could also be interesting to make them stateful instead of having only a hand-picked set of history-aware predicates such as store changed. And then a static analysis, it could be quite interesting to go back to a particular step in a static analysis and see what was going on there. So some kind of time-traveling debugging could be interesting to be introduced there as well. So in conclusion, we had 3 challenges that we would like to solve, which was the challenge of 2 code bases, the challenge of having this abstract domain and the exhaustive behavior of the static analyzer, and then the problem of having too many iterations before the bug is reached. To solve this, we introduced domain-specific history-aware cross-level breakpoints that allow the developer to reduce the state space where it needs to search for the bug and find the root cause of the bug faster. Thank you very much.
Questions, please come up to the microphone. Thanks very much for your talk. It reminds me a little bit of Code Prober, right? That in attribute grammars where you can look at the input program and then move around and see what are attribute values on that part of your tree or property. And so, you know, that was another case where you're looking at the input to your system and searching on it instead of in the code of the system.
So, but here you're doing, is it mostly abstract interpretation? Is the sort of things you're thinking with these breakpoints that as you're abstractly interpreting the program, that's when the breakpoints trigger?
Yeah.
So
yeah, the abstract interpreter traverses the program, and then when it finds the breakpoint, it will suspend the analysis based on the condition. So that's what we mainly focused on. However, you could also implement different kind of analyses using this approach, and also perhaps this approach can also be applied to a certain sense to, I think it was attribute grammars or something in the code prober paper. So yeah, that could be very interesting to see what the synergy between those two approaches could be.
because you're not. I was just thinking if you're doing something that's more syntax driven,
Yeah.
then I'm not sure what the breakpoints are as much, right? That you sort of aren't evaluating in some way or interpreting the program, but I don't know. It's yeah, I suppose if you could label a statement, say now when you do something here, right, as opposed to an execution style. Okay. Anyway, thanks. It's very interesting.
Could you share some thoughts on, well, I mean, in general, you call it static analysis, right? But in general, this is applicable to pretty much any language processing, which is hard to debug. So quite often this is done with some kind of traversals or strategies or some sort of abstract way to say, this is what I want to do with this data structure. And yeah, it would also be nice to have some debugging capabilities when you can say, well, I want to rewrite it innermost, but after you've rewritten it 3 times, then please let me examine what you've done. So is that the kind of direction where you think of going, or is it impossible to express in your way, or what are your thoughts?
In a sense, we have these breakpoints that consider previous states and histories and so on. And so in that way, you could think about changes in data structure and so on that could also be used using these breakpoints. But like directly, I don't really think that there is an application. But yeah, I mean, the approach itself could be used further. What I would also like to talk about maybe is, because you mentioned that it could be applied more generally, is that you have kind of the same problem with just concrete interpreters, for example, where you want to debug those. And there you have a similar approach in other papers as well, where they...
Some of them seem to have to do with not triggering recomputations, and were there other kinds of bugs that also appeared?
Yeah, so, well, we didn't really have that many bugs to create a very big or large classification, but indeed we saw different kind of bugs. So the one that I showed was about non-termination, but what we also frequently have in our static analyzers is problems with the abstract domains and abstract values. If you implement your multiplication in the wrong way or some other primitives, then that might also have some very strange results on the analysis implementation. So I think termination is an issue, the abstract domains are an issue, and yeah, currently those two are the most frequent bugs that we found in a static analyzer. So something about the soundness basically and about the termination, that's what we usually see.
Thank you, Vadim. Who will connect? Yes, I believe I will.
No emails? Okay.
That's always good, isn't it? Okay, thanks, Vadim. I'll be talking about enabling technology for live programming and about a meta language I constructed for doing that. So let's start with live programming. Live programming empowers programmers with immediate feedback about gradual changes to the code. And key are input mechanisms that let programmers perform what I call coding actions, valid changes to the code. So syntax errors are not coding actions. And feedback mechanisms that allow you to perceive what the effects are and evaluating if an action was successful. So let's go to a coding cycle. It starts with intentions. The programmer performs actions via some input mechanisms. This has an effect, which is quantified, and then it is displayed in some meaningful manner via a mechanism, interpreted by the programmer, and then evaluated. And then if you're not a very experienced programmer yet, you discover that you haven't yet achieved your goal. Of course, experienced programmers have amazing mental models. They predict many things correctly, but even experienced programmers do make mistakes. The idea is that live programming speeds up these cycles, and it has compelling benefits, namely you form mental models, your predictions become more accurate, you learn cause and effect relationships. And this is a very important thing for live programming, that you actually see why something happens. And you can ask why questions about it. And that allows you to predict the effects of your decoding actions and make targeted improvements to the code. So the research focus in this talk today is about running programs, live programming, that keeps test cases running and domain-specific languages to deliver feedback that appeals to the imagination. Now, the challenge is creating DSL interpreters that power live programming environments, and that is complex, time-consuming, and error-prone. I will show that a bit later. So there is a problem of that there is no enabling technology. The generic language technology for developing change-based interpreters is really available. So we need abstractions and techniques for constructing such domain-specific languages, and these languages need to have runtime state migrations and support scenarios with eventualities as fixed points and to express trickle effects. So I will be talking today mainly about the effects and not so much about the mechanisms. I had to talk about that yesterday. So let's go to an example in game design. So this is a tiny live game engine, and what I explained at the CVE Open Day, our institute had an open day, many kids came there with their parents, and I explained game design to them and actually let them do live programming. And I will explain it a little bit to you too. So many games can express their rules as internal economies, and those are a bit like marble machines. And game design is about designing such a marble machine with interesting chutes and levers and designing trade-offs. Where can the marbles roll? What can you choose? What can you buy? What can you collect? And playing such a marble machine, then the player decides what they do with the marbles. And for the kids, that was more or less sufficient to explain to them what game design is about. On the left, we see an actual marble machine, and on the right, we see a figure that formalizes it in a domain-specific language. And actually, it is 10 years ago that I first presented a paper at SLE about this particular DSL, so it's quite some time ago. And let's go to the engine itself. So it's called V. It reduces design iteration times. It allows designers to simultaneously prototype and playtest the game's mechanisms, and it enables live programming, or it is live programming. Changes have immediate effects, and there is immediate and continuous feedback, and it demonstrates runtime state scenarios. So now I will do something dangerous, which is to actually perform live programming live in my presentation, which, as we see, oh my God, my code is here. Yeah, this is awful. Okay. Never live program live. So, it didn't do that when I first presented in another place. Yeah, I should have debugged it, thank you. Yeah, that's what I'm trying to do. Let me see. So where is the mirroring thing? Anyone have experience with this? Arrange, mirror. Do we know this? Where to click? So your live programming environment runs well, and then you wonder, how do I put it on the display, right? I thought the calamity would be inviting the demo effect, not actually. Could I get assistance with getting it to mirror? So I'm trying to mirror what I see on my own display too. So I can change the arrangement, but
Okay, the cursor isn't showing.
well, yeah, it extends the display
Okay,
instead
yeah,
of
no.
mirroring.
Okay, so you can put it here. So we're sort of debugger.
Ah,
yeah, wait,
you
this
want me to do it like this? No,
Yeah,
I
it's a
can't
little
because
hard.
I need to see it on my own screen.
Okay. Okay, let's go back to displays.
Yeah.
Yeah.
Try to open settings and there are display settings and you can mirror here.
Mirror for this one. Does that work?
Yeah, finally got it.
Okay.
Thank you. Thank you for suggesting that. That was helpful. Okay. Wow. The number of pixels is quite a lot lower than I had hoped. Let's see if I can fix that. Yeah. No, apparently not. So. Well, let's just start. So it's designed for a phone which apparently has about 4 times as many pixels as normal. But okay, I'll start the demo. It's about a girl who lost her bunny. I use this for the open day. And you first click on the circle, then you click on the screen. A circle is now on the screen. What is this? This is the place where marbles can reside. And we can let the marbles roll here. I cannot fully edit it because it's not fully on the screen, but I can add a rule that allows a marble to roll here. And if it rolls, then there is a marble. And when a marble is in the pool, the girl has arrived. I can add another rule that allows her to leave and also make that interactive. We get another button, and now we have a tiny way for the girl to go and leave. Then I can add another node that every time she arrives, she brings an apple. And now I'm running out of screen space because of the insanely low amount of pixels. Okay. So every time she now arrives, she brings an apple. And we can see that here. So now she has apples. And finally, to wrap it up, and let's see if I can do that. I add a way for her to exchange these apples that she has for her bunny. So the marbles are rolling while the software is running. See, actually, live programming is much easier than setting up your display. Yeah. So we now have a tiny game, and we can rearrange the button so that it even fits on this tiny area. Look, now she has 2 bunnies. That wasn't the story, but you know, she exchanged another apple. So what can we learn from this? Well, that we have a running game economy, and we have a marble machine that basically runs while we're playing with it. It is live programming because it integrates runtime state and effects and feedback all in the same view and in a rather understandable manner. We don't have to press run or execute things. It just always runs. Well, that was the tiny thing I wanted to show. Next time I will make a movie again and not do the live programming. So I will not switch my display setup anymore. So how to construct such a DSL? I now explain my problem. I guess I'm almost out of time. But so for providing live feedback, such DSL designs must account for runtime eventualities, and those are valid changes to programs and runtime state. So, and they have to represent a multitude of valid executions and dependencies between the changes to the program and the runtime state. And yesterday I talked about how to use Godot to create this tool, and today I talk more about effects. The objectives are to address the lack of enabling technology for creating change-based programming environments. The approach is to create a meta language that speeds up the development and it powers the interpreters. And yeah, we validated on existing DSLs. There aren't too many that actually work like this. The first one is the live state machine language, simultaneously running state machines and editing them, migrating the current state, say if you delete the current state, things like that. LiveQL, actually yesterday there was the most influential paper award for this state-of-the-art in language workbenches paper. That's where QL originates, this questionnaire language where there's a live version that if you answer a question, it can have effect on the visibilities of other questions and computed questions. So it's actually a kind of, yeah, an iterative, you have to compute a fixed point for getting all the answers again. And so this is quite an interesting case study. And finally, the live micro-machinations language, which I just showed you about game economies. Let's talk a little bit about framework, if I have the time. It's called Cascade. I put a couple of snooker balls on the table there to illustrate the idea that these effects, they cause each other. So you can understand them like that. So Cascade is a meta language. It expresses change, cause, and effect. And it's intended for the design of DSL interpreters. It's a Rascal program, the compiler of, well, just 300 lines of code. It generates powerful interpreters, the driving force behind live programming. And at runtime, these execute transformations in sequence and produces transactions that consist of edit operations. Upon completion, these interpreters commit the transactions to the version history as cause and effect chains, which facilitate answering why questions. And the Delta runtime runs on C#. That allows me to integrate it with Godot. And it's almost 6K lines of code. So the meta language. So it expresses the states, the syntax and the runtime states as meta models. The actions and events are bidirectional model transformations that support exploratory coding. It has side effects before and after every event, and the relationships can have predictable outcomes to steer the behavior so that when we're live programming, we can learn about how these effects cause changes. And the key is, of course, the cascading changes. These are central to live programming to express these runtime state migrations and account for the eventualities. Now, here's an example of the meta model of the tiny live state machine language. You see on the right the static meta model and the right the runtime meta model, which kind of extends it, but in this case, it's a one-to-many relationship. You can run it as many times as you want. A little bit of code, because of course we're at SLE. You see here the implementation in Cascade of the Mach class, a bit of it. So you have attributes like you expect, but then you see an effect, which is actually a bidirectional model transformation with a future keyword. It promises that in the future there will be an object of the class Mach, and it has to have a name. And after executing it, there will be a machine. The opposite, or the inverse, is an effect that deletes this machine. It promises that it will exist in the past, but no longer in the future. And it also cleans up the states and the instances if you shut it down, so that you will, again, have a correct runtime state. And with these pre and post clauses at the bottom, you can steer it. So the user interface, of course, you need user interfaces for live programming. I just showed you the Godot one. So you can develop your own, or you can use the built-in read, eval, print loop before you have a custom UI. Okay, so here's an example of the REPL. So here you have a REPL, and these are sequential commands. You can declare some variables. Here you create a state machine. by simply giving parameters and then pressing enter. This hooked arrow is an enter. And then finally, you can print it by querying. So that's simulating the feedback, and we see that a machine called doors is being created. You can also use the REPL to run it and then create an instance by calling that. And then you see that the little star shows it's now in the state closed. So when you start it, it will be immediately started in the initial state. If I would then remove it, it has no longer a valid state, so you have an invalid state machine. But okay, it will try to migrate to a state. So the Cascade framework generates interpreters, and this is the driving force behind live programming. The Delta environment integrates these DSLs in a common runtime, and it schedules and executes events, and it performs these bidirectional model transformations and state migrations. It maintains a version history and a heap, and it updates syntax trees and runtime states, and it generates, and this is key, the effects of the transformations as historical transactions that are captured as edit operations, and it preserves the causal relationships that we need to answer these why questions in cause and effect chains. And it schedules them so that you can get very complex cause and effect chains, so the control flow is generated. Here's an example of a simple transaction. These are actually edit operations encapsulated in a create event, and they just express what the change is. Here's a more complex one. You can't really see it, but you see all kinds of nested pre and post clauses. This is actually deleting the current state of a state machine, and there's running state machines that then all migrate, and in the end you end up in a new valid state based on all the side effects that are programmed. So some results in these case studies that I did. The volume of the specifications is considerably more concise than the originals. The Cascade specifications are small and understandable. They add traceability for cause and effect of all actions, of all changes that happen. It's rather expressive. It can express evaluations as fixed point computations because you can schedule future events to happen. And that's necessary for fixed point computations because you need some moment that you check, am I done or do I need to go again? And by scheduling these future checks, you can then sort of get this cycle to execute again. And it helps a lot with the maintainability compared to the original specifications. It reuses side effects and it expresses them in an understandable way. And it's good, well, it's relatively straightforward to use Godot to create front ends. Both have event APIs. And the benefit of Godot is that this tool that I barely got running in this presentation runs very well on my mobile phone. So yeah, but that's a benefit of Godot. They deserve the kudos for having such nice cross-compilation. So wrapping up, so the objectives were to address the lack of enabling technology for developing change-based live programming environments. The approach is a meta-language that speeds up the development of DSL interpreters that power this live programming, and validation 3 case studies, the state machine language, questionnaire language, and machinations. And future work, and I guess this is also why I'm in this session, omniscient debugging. I want to have an omniscient debugger that uses these cause and effect chains, because then I have a reusable debugger for each of these DSLs that I build. Of course, I also want to analyze the Cascade specifications. Part of them can be generated. Do they have the properties that are intended at the language design level? And can you prove that valid states result from them? And of course, generating the visual interfaces as well. The one I showed for the machinations language was created by hand, and it would be nicer if, they could also be generated. And that wraps it up. Thank you for your attention.
Thank you very much. We have time for questions. Please come up to the microphone.
I don't know much about this change or events thing that you were telling, but basically, does the framework that you're presenting, it's using deltas in order to implement
Yes.
to manage the runtime? And how
Yeah,
does
so
it,
you just
does it scale? Don't you get like
well, for now I'm building
deltas and
of course it's intended for live programming, so it should be immediate, right? I didn't do any speed measurements on it, but so far the experience has been immediate.
okay.
Yeah, I'm building DSLs with it, so it would be interesting to see, can you build bigger languages with it? Of course, it has a slight overhead because it reflects all the changes at runtime, and it has to generate edit operations, these deltas, and execute them. And of course, it maintains its own heap. So there is bookkeeping going on, and that costs extra time. And there's no checks in place, so if I have cyclic dependencies, my scheduler will never stop, things like that. I have to.
But I guess it's usable and you don't have like functional problems because of that. It's not like
it's already a practical solution. Yes.
Yeah, okay.
Yeah.
Thank you.
Thank you.
Yes, thank you very much for the presentation. You had the slides where you showed some cascade code with effects and inverse effects.
Yeah.
Can you go back to it and explain a bit more precisely what triggers the execution of those effects and inverse effects during a live programming session?
Okay, thank you. Very nice question. So let's say I click on the screen and I create a node, then it would call one of these create effects. Basically, those events are mapped. Some of the effects you can't directly call as a user, right? So this create effect here is, let's say, it's a coding action. It changes the syntax, and then it affects the running program by updating the syntax, but it can have effects on runtime state information as well, that as user, well, while programming, you don't directly manipulate that, but there's other actions, like user actions, that can then trigger a running program to do stuff as well, like pressing the button. Pressing a button will call an effect that calls the evaluator that then calls more of these effects to happen. And so, yeah, does that explain it a little bit?
Yeah, very good. And small follow-up questions. What I'm seeing here is not code that will be actually executed by an interpreter. This code will be translated into edit scripts, and this is what is actually
yes.
I mean, the program is patched based on what's generated from those implementations that are actually edit scripts.
Yes.
Is that it?
Yes. So what you see in the curly braces of create, those are what you could call an edit script, because it binds at runtime, and then it becomes edit operations. So the edit operations just describe change, like deltas, and here you actually, so let's say when you delete an object, you don't say the class, but it's an implicit parameter. So that delete and create are inverses of each other. And the assignment that you see is actually a replacement, but I'm not typing the current value there because then I wouldn't be able to execute it in different contexts, right? But when it then makes the edit operations, it generates them and it immediately applies them like updating an object-oriented database. Yeah.
Okay, thank you.
Thank you.
Thanks for an interesting talk. I have a question about, as you're sort of live programming, editing things, you must sort of get into a state where the thing you've built, the state machine or whatever, is not executable.
Yeah.
And you sort of have to get to the point where it's then executable again so that you can observe it sort of running. Is that?
Yeah.
Is that, and is there a, I mean, I was just trying to think if I was trying to use this to build a simple functional programming language so my students could write their little OCaml programs and watch them run, right?
Yeah.
And then what are the effects and inverse effects are adding to the program, I guess, that they would sort of, or is it mapped down to characters as they're typing and deleting characters in their window.
So
that seems like very fine-grained as opposed to something that is more coarse-grained, which these feel like, where you've created a construct in the program.
Yeah.
Here you're building a machine or you're building a state as opposed to beginning to draw the circle that is the state, right? Which is a very simple action that eventually gets you to the circle that is a state.
Yeah, these are the abstract coding actions and runtime transformations that happen. Indeed, typing in text, if you would fit a textual front end to this where you reparse every time, then you have to perhaps do differencing, like differencing and then finding out which parts are added, and then finding out which actions to execute, what has actually changed. But for me, the truth doesn't start with Git changes. Those are inaccurate. It starts with what the user actually does when they change things. And yeah, so it means that expressing changes to these little programs, update it in a meaningful manner, and that each of these changes, whatever you want to communicate back to students who are building their little camel programs, yeah, you can design the effects in your meta description to inform them what does it mean what I'm changing, so that they have some intuition of what the concepts they are operating on do when they run. And when you have more, let's say, imperative languages, then you need constructs to map that, like probes, to get an idea of the big distance between the execution model and the runtime model. And what I'm trying to do here is to shorten that distance. That's why I scoped it down to DSLs, because sure. This mental distance is lower.
But they're DSLs that have sort of, I guess for me, more easy to understand creation and deletion activities.
Right.
Make a state, remove an edge. Those things seem like a crisper. They have like a more direct, I guess, in my sense. So there's an effect, or you delete it, and the actions are very clear. Where if you're typing code, you somehow need to match those edit actions in the window to
you have
in the abstract syntax.
Sure, but so if you want to use Cascade in that context, then retrofit an algorithm to it. Like many years ago, we did a thing called textual model differencing, and then it calculates the changes. And once you know what the change is that is being performed by the programmer, then you can cause its effects or enact its effects by running it on the interpreter. But yeah, if you want to have a textual front end instead of the nice visual one, then you need to do the parsing as well.
Right,
yeah.
Right. All right, great, thanks.
Thanks.
Thank you. Let's thank the speaker once again. And this concludes the session. Thank you very much. Coffee break. You deserved it.
Oh, wait, no. Oh, this one. Touch. Okay, all right, all right. Good morning. Thank you for inviting me to give this talk. I have been, in the past year or so, maybe a little less, sort of dived into the new world of large language models, like a lot of people, I'm sure, to figure out what the hell happened when I was not paying attention, I guess. And I must say that I'm quite sort of surprised, overwhelmed, excited, everything at the same time. I am on the camp that this is indeed a discontinuity. It's definitely something that is going to change a lot of things, a game changer, including in our little world of research in programming languages and in software engineering, for sure. Not to mention just the things that can be done already for software development, the tools that can be done to aid software developers, but it affects also what we do in research and how we think about the problems that we have become accustomed. So the title says it all. I think that, and when I say artificial languages, I mean a broad class of languages that are designed by people, as opposed to natural languages that have been emerged organically among humans. So in artificial languages, I mean programming languages, data structure languages, specification languages, you name it, everything that is on purpose designed by people. And I think that they are dead as we know them. But on the other hand, I think that there's a new era of interesting things that can be done. And basically, artificial languages are not dead. They just are going to reincarnate in something completely different. So that's what I want to talk about. So this concept of programming is the art and science of automating processes, right? We've been doing that since we have computers. And the way that it works is we take some ideas that are fuzzy in somebody's head, and we produce computer processing instructions or specifications. Could be something that is artificially specified. And this process, since computers were invented, has been done by people. There's a person in the middle that takes that idea and writes down some, in some artificial notation, those ideas. And what that produces is artifacts that hopefully are well specified, well formed, that they obey some specification, there's no ambiguity. That's what we want, of course, in practice. We all know that reality is a little bit more interesting than that. But that's the goal, right? We want the artifacts to be totally under our control, and we want to know exactly what is it that the computer is doing with the specification that has been produced. And so these artifacts end up in some form of an artificial language. It could be a programming language, could be SQL, could be JSON, could be any of the many domain-specific languages that are out there. But it's basically something that typically textual, although there are some graphical notations out there too, but this is what we have become accustomed since computers were invented, right? Our generation has grew up looking at problems of this process, right? And all our research questions that we have been looking have been, well, how do you specify this? How do you make sure that this thing on the right doesn't have bugs? How do you make sure that it captures the person's intent? How do you make sure that it, cooperates with other, interoperates with other pieces like this, all sorts of things. That has been our field, right? But the interesting thing is that can we automate that person in the middle? And can we remove the person out of this loop? But this is not a new question. So first point that I want to make is that this is not a new question in this age of LLMs. This is a question that has been looked at since the beginning of computers. In fact, since the beginning, we had the spring of programming languages in the 1960s, where compilers were, invented in a way. They were blooming. The need for compilers was very obvious at the time, and compilers are, in many ways, a way of automating some of what people were doing. Right? Translating something that is a higher level to something that is a little bit more low level. That has been replaced. It was made by people, and at some point it has been replaced by a tool. And this continued. In the 80s and 90s, we saw, again, these ideas of eliminating people from the loop popping up in case tools, generative programming, a lot of it coming here from this community, right? Program synthesis, more, it's an old idea, but that has been always there, picking up its head from time to time in different kinds of communities. More recently, efforts like low code or no code, all of that have been approaches to the same question, which is, can we remove the person out of that process? So the question is not new. But however, from playing now with these large language models, it seems that there's something qualitatively different that is happening now. That, yes, things have been sort of progressing about eliminating people from the process, but I think we're going to see something really completely like, that we were not kind of prepared in a way. In many ways. Now, of course, again, we also always have to see these exponentials in context, right? Because that's the way that history goes, right? There's a discontinuity, and then there's things kind of even out. There's a stable period for a while, and then there's another discontinuity, and so it's nothing that hasn't happened before. In fact, in my adulthood as a professional computer scientist, I remember some of these things. Like, for example, I don't remember the invention, and I don't remember the von Neumann computers. I heard about them, but I clearly remember, and so do many of you, the invention of the web in the 90s that felt like one of these. It really felt like that was something that was going to change things. And indeed, it did. It was a very rapid adoption. Things started to change all over, like things that people had been talking for at least a decade or more, 2 decades before. People were talking about distributed computing and how to make these kinds of decentralized, interoperable nodes and stuff like that. Had it all been, it's not new, but suddenly the web came out, and it basically fit on something that people were, in a way, predicting that it would occur, but not knowing exactly the form that it would take. And it took the form of the web. It was kind of interesting. And now, I think that large language models are one of these. So in that respect, I want to talk about some of my explorations and some of my students' explorations on this brave new world of LLMs, starting with everybody's entrance to this world, which is chatbots, ChatGPT. But then quickly, if you are a curious person, quickly realizing that ChatGPT is kind of boring and limited, and we want to do a little bit more. So you start lifting the veil, and all sorts of things, interesting things pop up there that make you realize that you can actually develop applications that are powered by LLMs, components that interact with LLMs, and that you can feed things, you can have feedback loops in the process that make things really quite amazing. So in that vein, I'm going to talk about things like prompt engineering, multi-step prompting, semantic retrieval, and all those things that I'm going to sort of explore. So let me start with a live demo, and of course live demos are always dangerous, but I'm going to try. I am going to interact here with ChatGPT. Let me put it here. And of course, in presentation is always a challenge because I see something in that screen that's not here. So hopefully this will work. Hold on. All right, so let me do something here, which this was one of my first experiments with ChatGPT. Well, it was the second experiment with ChatGPT. I wanted to see if ChatGPT really could help me write something that is not trivial. That was my my second interaction with it. Hopefully, this will connect. Let's try again. Do I have network here? Hold on, let me just see if I'm connected to the network. I think I am. Okay, here we go. All right, so I wanted to write a tokenizer with ChatGPT, and for many of you, you know tokenizers. They're sort of the first step of any language processors. You have to tokenize the text and produce tokens, and then feed them to the next thing that comes, maybe a parser or something like that. So, I wrote this blog post when I made this experiment, but then I also use it as sort of a script that I can run. So here's what I told it. I don't know if you can read this. Can you read this back there? No? Yes? So I said something, help me write an interpreter for a scripting language. I want to write interpreter in Python. To start, give me some code for a main function that checks whether there is a command line argument. If so, it reads the file given in the command line and runs it. If there is no command line argument, it goes into interactive mode, prompting the user for lines in that program. Everybody kind of recognizes this little cycle, yeah? So it's sort of the main function. Let me copy this here, and now let me go here into ChatGPT, and I'm just going to do the same thing. All right, so let me do this. Sure, it is. Okay, and it gives me the code, and it starts explaining what the code does. I don't know if you can see. Is it possible to turn off this light over here? Because I have everything in dark mode. There you go. Better. It's better? Yeah. All right, so it gives me a program that it looks like it's doing what I asked it to do. So it checks if there is a command an argument. If so, it opens the file and calls, for each line of the file, it calls execute line. Otherwise, it goes into a while loop that asks the user for input, and it executes the line. This seems great, right? This seems good. So what I did from then on is that I would just copy and paste the program that the bot gave me into a Visual Studio and test it. Does this work? And then I went it from there, doing things like, okay, great. So now let's focus on the execute line, right? So one thing that I wanted it to do, so it's a conversation, right? So something like that. Okay, great. Let's work on the run. In that case, it was run code. In my case, it's execute line today. For now, it should scan its input for a sequence of token and simply print those tokens out. I just want to know if there are going to be tokens, and I just want to print them out. So this is an iterative development, right? I don't know how you write programs, but I tend to write programs sort of like, okay, let me sketch sort of the main function over here. Now I'm going to zoom down and zoom in on some function, and going to zoom in on some function, and zoom in on some. That's sort of the approach that I'm taking here too. So I could do that one more time here live, see what it does out of that tokenization. So let's work on the run. No, it's not run code. It's what's it called? Execute line. Let's work on this function. For now, it should scan the tokens, and okay. So then it zooms in on the execute line. It also suggested some tokens already. I didn't ask it to do it, right? It's already suggested some tokens and how to parse them. I did not specify this, but it just decided to give it to me. Okay, I can work with this. Fine. So I would just copy-paste this function to my Visual Studio Code and check that it does something and continue from there. And you can continue, and then I can say, okay, I don't want those patterns, okay? I want some other tokens. Give me some, for example, the next thing is give me a class, give me an enumeration. Here's what I told it. Give me an enumeration of, give me an enumeration that has the following classes of tokens. So single character tokens, 1 or 2 character tokens, literals, and keywords, and the end of the file. Okay, these are my tokens. I'm designing a language. I know what tokens I want, right? So ChatGPT gave me a little language that it thought I wanted, but that's not what I want. I want this language. So I can say, okay, let's try to do this. So I can specify what I want, go back over here. And it gives me actually a lot more than, well, maybe, a lot more than what I asked for. A bunch of keywords that I didn't ask for, but that's fine. Literals, 1 or 2 character tokens, single character tokens, things like that. And so the conversation continued. You can read my blog post. And at the end, I ended up with a program that indeed tokenized according to the tokens that I wanted, and it worked, right? So it was like a programming buddy. It was like a junior assistant. I was asking, I was designing the language. I am designing the language. I am designing the tokens that I want. At points, I actually tell it, look, this is not how I want it. Do it in another way. And it just does it for me. So it's quite remarkable. And at the end, you end up with a program that actually does exactly what I wanted it to do. In fact, the bot at some points corrected me. I was giving it wrong instructions. I was calling some token something bang, and it was not something bang, it was something else, and it corrected me. So that is quite an eye-opener for me, that you could indeed do something. Hold on. Yeah? There you go. Okay. Where am I? Okay, all right. I think I lost the control of the PowerPoint presentation. How do I? Go here, maybe? Okay, all right. Do it again. Okay. So this is probably the experience that many of you may have had when OpenAI came up with ChatGPT. You know, let's try my little pet program, see how it does on something that I know very well. And I mean, I don't know about you, but my reaction is like, holy, you know, this is amazing. What's going on in here, right? But then it quickly, you know, as you start digging deeper, you quickly become aware of it. It's like, you know, it's like my dog, whenever it goes to a new space, the first thing that it goes is figure out the perimeter, right? Where are the boundaries, right? That tends to be what I do too. So where are the boundaries? Where fail, and where does this lead me? How does this new world look like? What's the geography in here? So another thing that started coming to focus is that the response of the chatbot depended a lot on the words that I used, like the choice of the specific choice of words, even the sequence of words. The answer would be different depending on what I would ask it. So let me give you just an example over here. And here I'm not going to use the chatbot. I'm going to use the OpenAI platform, for those of you who already also found that, the playground. So here's an example of oops, you're not seeing this. Hold on. Okay. So it's an example of a piece of work that I did with some of my students, which was to find out if GPT could generate commit messages automatically, given just the diffs. Okay, just give it the diffs, no more context, just a diff, and you ask it, generate the commit message for this diff. Okay, and by the way, since you're at it, let's see if you can also provide some sort of justification, which is, you know, in the principles of good commit messages, is that it should say what changed and why, right? It should be a two-part kind of thing. So we experimented with a couple of prompts. So the first prompt that we experimented was something like this. So let me write it here. Generate a commit message for the following diff and provide a justification for the changes. And now I'm going to put a diff in a large diff over here. Doesn't matter, you don't need to understand it. So bang, there's the diff. So notice the words that I use is generate a commit message for the following diff and provide a justification for the changes. So submit. All right, so that seems like a reasonable commit message. Refactoring config settings for token obfuscation and adding support for subtoken creation. Great. And then it goes on to the justification. And it goes on and on and on. And I'm thinking, look, don't lecture me. This seems a little too long. You know, I don't want to have this in the commit message. So how do I make it that it's not so long? Okay, so how do we make it that it's not so long, but it's still meaningful, right? Okay, so we experimented with another prompt. This prompt was almost the same. Generate a commit message summarizing the modifications made in the diff, accompanied by a brief rationale for the change. So we changed the justification to rationale and added the word brief, and also the message, we asked it to summarize the change. So a little bit nudging towards, you know, don't spam me kind of thing. Let me put the diff again. Okay, reorganized token obfuscation settings and added subtokens option to tokenizer. All right, it's a little shorter. It's only one paragraph now of the rationale instead of several paragraphs. That's progress. And maybe I will be able to read this when I'm looking at the project history. It just explains, does it have the, yeah, it has the rationale, right? So in an effort to simplify our configuration and add new features, that sort of feels like rationale. Why did we do this? And why did we add the token section? This setting provides the option to split the tokens on camel case. So there's a little bit of a rationale. So this change at the bottom line, this change will give users more control over their tokenization process. Okay. So we made some sort of a controlled experiment. We took many commits, so lots of diffs. And we had GPT-4, this is also GPT-4, generate commit messages with rationales for, and then we looked at each of them individually to see how well they actually captured the diff, whether it was true or not, whether what the GPT model was saying about the diff was true or not, and whether it was kind of hallucinating, you know, or what were the problems that came from using the model to generate commit message. It turns out that it's pretty amazing, pretty good. It has some problems, but not many. So for the most part, vast majority of the generated commit messages were actually correct, with good rationales. And the few problems that existed was sometimes it says a lot of truisms, like stuff like this. You can see already, this change will give users more control over their tokenization process. Okay, you could avoid that sentence. It's not necessary, you know, for us, right? And this is not so bad. There are other truisms that are even totally redundant. You shouldn't say that. So it's a little harder to control those truisms. But for the most part, it actually did pretty good at capturing the essence of the diff. And the other interesting thing is that we then compared to the original commit messages by the developers. And you're not going to believe what happened next. These messages were actually better for the vast majority of the commits. And it's not that, a part of the reason why they were better is that because the original commit messages are really bad. As you probably know, who hasn't written that awful commit message like update something, you know, minor tweaks. You know, or something like that. Like, it doesn't say, we know that we should be descriptive of what happened, we just don't have the time. So because a lot of commit messages are bad, a lot of the original commit messages are bad, actually these kinds of explanations and rationales end up being actually better than the original. So that is quite amazing. But the point why I'm making this, the main reason why I'm showing this piece of work is to convey the message that the words that we use, what we ask the model to do, matter a lot. Every single word matters a lot. So now it's become a really weird engineering situation, which is what words do you use and why? How do you justify the words that you use when you're doing some research, for example, and you find out, you know, I'm going to ask the model to do this, so I'm going to just blurt what comes into my mind. No, you have to justify why did you choose those words? And what words did you try? And what happened when you try different words? Right? It's an interesting thing that has become apparent, at least for research and for, you know, reproducibility and understandability of things, like why these words and not other words. So this is one interesting thing. Another interesting thing that happened, this goes into the idea of what has become known out there as prompt engineering. You probably have heard this term. This started, 2 years ago with like prompt hacking, right? You just switch words or put some like code words in the prompt, and then you figure out if the model responds better or not. But it has become more of a systematic practice, and now it has the term prompt engineering. These are methods to steer the model's behavior for desired outcomes without updating the model's weight. So the model is fixed, right? It has been trained. We're not changing the weights, but we want the model to behave in a certain way. We want to steer it so that it produces a certain outcome all the time, rather than something that we don't control, right? So every word matters. But the other thing that started to become apparent to me is that while these models do pretty good with the programming languages for which there is a lot of data out there, like Java, C++, Python, it's fantastic. There's clearly limitations when you start wanting it to generate programs in languages that it hasn't seen a lot. And that's where things become really interesting. So we were looking at another study in my group, which is to, okay, this is the automatic commit message. Yes. Which is the Daphne. So Daphne, you may know, it's a programming language, functional object-oriented imperative programming language designed by Microsoft Research that has formal verification and works with a theorem prover on the back end. And so you can write provably correct functions, they call it methods, in Daphne. So you write imperative code, and then intermingled in the imperative code, there are formal specifications and then proof annotations that help the verifier prove or not what is it that the formal specifications does. Needless to say that these models have not seen a lot of Daphne. In fact, when we went to GitHub, we found only about 200 or so Daphne projects, which is close to nothing, right? So there's not a lot of Daphne code out there. So but nevertheless, it tries and it gets some things right? So let me show you here. Let me get rid of this. Let me show you an example. So we started asking it to generate some things in Daphne. So here's a prompt. Write a method in Daphne to find squares of individual elements in an array. No more context, just what we want. Okay, just saying, give me Daphne code. Okay, so it tries, and it surprisingly knows quite a bit. It knows that the functions are called methods. These imperative functions are called methods. It knows that it has these annotations. I'm going to let it finish. Okay. It knows that it it hasn't finished. Okay. And now it always likes to tell us, to lecture us what is it that's happening here. Okay, stop. All right, thank you. So it knows about these pre and post conditions. It knows about hopefully the type system, right? It knows what types there are in Daphne. It knows quite a bit, considering that's not a lot of Daphne out there. It surprisingly does not completely mess up. But of course, you can try and then go, copy paste this into a Visual Studio. Sorry. try to do this and put it into Visual Studio here. Let me put my Visual Studio here. Oh, actually, you know what? It actually verified. It's quite amazing. For those of you who don't know Daphne, you put it in the Visual Studio, and if this line is green, if you see this green line, it's because it's verified. Okay? So it actually, amazingly, it verified, right? It has the post conditions, you know, and it's a strong post condition. It ensures that everything in the output is the square of the input. And it has all the invariants and everything. It actually got it right. Okay? But that, you know, this is a relatively simple problem. So let's try it another problem over here. So let's go here and give it something that's a little bit more complex. Okay, something like this. Write a method in Daphne to remove characters from the first string which are present in the second string. That's a little bit more complicated. So it really loves lecturing. That's for sure. Okay, you're already seeing, for example, that this one, it doesn't even try to give us the formal specification. I'll go back and tell you after it finishes lecturing us. All right, so let's see what happened over here. So it gave us a method indeed, a method remove characters from, you know, two sequences over here and returns another sequence. But as you can see, there's no pre or post conditions. And without post conditions, this is basically trivially verified. It verifies because there's nothing to verify. So that is not ideal. Let's put it this way. Yes, this may even actually be correct. I don't know. Maybe the syntax may be correct. Let's try. Yeah, okay. The syntax is actually correct, which is amazing. And it's green, but it's green because there's nothing to verify. And that defeats the purpose. So we want it to write Daphne code. We want the pre and post conditions, right? And then the proofs that is actually correct. So this is interesting, right? Because you quickly start realizing, okay, so it knows a little bit about Daphne, but it doesn't know enough. And maybe it knows enough to give us the verified programs for very, very trivial problems, but for things that are less trivial, it just doesn't even try to write those formal specifications, right? And that's not what we want. So the question is, so at this point we have two attitudes. You say, okay, this sucks, okay, forget it. We cannot use LLMs for anything other than Python and Java. And there's nothing here for more interesting things like Daphne or other languages that we are all developing over here. You know, unless there's a gigantic database out there of examples, then these models don't know anything about it. You give up. And you say, okay, haha, great. I still have something to do because the LLM doesn't know my little niche language. But that's not the attitude that we took. The attitude that we took is that you can teach a pre-trained model after it has been trained. It's a very important thing to keep in mind. What the LLMs tell you after a very naive prompt is just the beginning of what it can do. Okay? Again, it goes back to the prompt. The prompt that you give it has a lot of influence on what it's going to give you back. So the question is, so how can we teach the model that clearly does not enough about Daphne? How can we teach it Daphne without pre-training it again or finding a gigantic database of Daphne programs and doing fine-tunings, because these models can also be fine-tuned. But it requires a lot of data. How can we do it if we don't have a lot of data? So we can do it, in fact. So here's what, it's a topic of a paper that's under submission, but I'll just give you a little overview of the approach. So what we do is the following. We have a small database of Daphne, verified Daphne programs that we wrote by hand. We have about 50 of them, algorithms of these kinds, right? So we wrote them, there's 50 of them. And now for every single new algorithm that we want the model to generate a verified program for, we do the following thing. We do something a lot more complex than what I've been showing you so far. So the first thing that we do is we take it step by step. So first thing that we do is say, okay, write in natural language, okay, in English, write down what are the preconditions and postconditions for this problem. Okay, given this problem, whatever this one for remove chars from one sequence that are given in another sequence, write in English the pre and post conditions. By the way, what I'm going to explain is very similar to how you would guide students, for example, how to solve these problems, right? So that's the first step. Now, once you have the pre and post conditions written down by the model, you want it to generate the code, but how are you going to have it generate the code? So here's what we're going to do. We're going to look into our database, small database of 50 examples, and we're going to find the 5 most similar programs to the new task that we are asking it to do. Okay? And what we define most similar, we match the post conditions, because the post conditions are the most important things in here. So we match the similarity of the post conditions, and we find the 5 most similar examples in our database. And then we construct a second prompt that has, okay, and I'll, okay, I don't have time to explain the whole thing, but here are the 5 examples. And now do the new thing that we're asking you to do. And believe it or not, we were able to get the model prompted in this way to generate another, forget the exact number, but it was like 100 or so verified algorithms on the, totally correct, with the right post conditions, strong post conditions, with the right annotations that the verifier could verify everything. Okay, so it's not as, the first reaction is saying, okay, so this cannot know Daphne, great, I'm going to give up, I'm not even try. That's not the right reaction. The right reaction is, okay, how am I going to teach it what I want? And interestingly enough, the teaching has a lot to do with how we teach students. That's the bizarre thing. It's really weird. The way that we teach students with lots of examples, meaningful examples, right? With teaching them to divide things step by step, that also works here. So it's quite amazing. So let me move on, because I'm getting... so what we ended up doing was this, I don't even know how to call it, we multi-step dynamic few-shot prompting with chain of thoughts, a combination of techniques that have been sort of published in the machine learning world of how to prompt these models so that you can get more out of them, that they actually didn't have enough data to start with. All right, so just just goes to, the important thing to note is that there's the raw API calls, one API call, one prompt of the model, but then there's all sorts of things that you can do around it, right? You can design an entire application that goes many times with different kinds of prompts, do this now, and then based on that, do that other thing now, and maybe now you also have a semantic database, a vector database, that you find similar things from there, and you retrieve them, which is what we did for the examples, and you add that in the prompt. There's all sorts of interesting, fantastic new worlds in here to have these very rich applications that take the most out of the models. It's not just what the model knows out of the box. So can we automate this? I think we can. Yes, we can. And we have been automating this, for many decades. But now we can really kick it. The last part of actually using sort of natural language to create programs. But there are some caveats. So let me talk first about the yes, you can. So the models know a lot already, as we saw in Java and Python and all that stuff. We don't need to teach it, already knows a lot. But they can learn. They can learn even more if you teach them appropriately. In particular, the examples work really, really well. And chain of thought and stuff like that, dividing things by steps. So yes, we can do a lot. So for popular languages, in spite of the models knowing a lot, you cannot trust blindly, of course. You have to check it, review it for accuracy, you have to test it. You cannot just take the model at its face value. For niche languages, simple prompting is not enough. So maybe you have a large database of examples you can fine-tune. If you don't, then you can do all sorts of combinations of techniques from machine learning that you can take the most out of the model by teaching it in the prompt itself. All right, so let me kind of get to the end of the talk. The Queen is dead. And I looked at I don't think you can read it, it's a little fuzzy, but I looked at the topics of interest of SLE, this conference. And I see things like software language design and implementation, approaches to and methods for language design, static semantics, techniques for specifying behavior, generative approaches, meta-languages, etc. So it's a long list of topics over here. I think a lot of these topics are, the traditional classical approaches that we have been kind of gently improving over the years are probably dead, because you can get a lot out of these models for actually helping you give solutions for whatever problems you are looking at. In fact, the whole thing about designing artificial languages may be put into question, right? Why are you going to design yet another language when you can actually have the people talk in natural language and then have some AI transform that to JSON or whatever? So the whole thing may be put into question. So you kind of have to go through all of these things and kind of question, okay, so what's happening in this particular topic, given that these models are so powerful? So these are all questions that we as communities need to do. There is a discontinuity, and there's a danger that we are kind of stuck in the old ways and sort of miss the train because the train has arrived. On the other hand, I think that it's a very exciting time because, it just turns out that the problems are still there. They just take a slightly different form. So, yes, what I just said, like, why are you designing new languages anyway? Because you can talk in natural language. Well, that's actually not true, as I showed you here. The words that you use matter a lot. So if you give a UI to some person and you let that person just use whatever words they want to use, chances are that that's just not going to work. And now what? Now we're back into the mode that we actually need to inject something artificial, right? We need to process the words that the user inputted or something, right? And we're back again to have to design something because, if you just let people just talk naturally as if they're talking to a person, that only works in very specific situations. So I think there's a lot of excitement in here. There's lots of interesting things in here. In all of these topics, again, you just need to look at them in a slightly different glasses, with different glasses for sure. So my very last message is that programming and the things that we do, it has always been, and it will always be, about effective communication, which, of course, is related to language. And effective communication is things that, yes, it includes notations, artificial notations, but it's not just that, right? We can all, this is a problem that exists, well beyond computer science. So people, when you have legislators that write the laws, there's an art to writing laws so that it doesn't become a total mess, right? That's why you call it codes, to some extent. Or any kind of specification, building codes, for example. There's an art and something similar that you have to be very precise. You have to communicate the intent really, really well. And of course, we in computer science have been used to doing that in super artificial languages that have an automated, executable semantics, and that is even connected to mathematics that can connect directly to theorem proving and all that stuff. We've been using to doing that. But I mean, the whole point is that it's about effective communication, that whatever the intent is needs to be communicated properly and unambiguously, and that can be done with super artificial languages. It can also be done with slightly less artificial languages, and there's a spectrum in here. And I think these language models now allow us to explore a lot of this spectrum over here. It's an interesting thing that is, I think, is happening. So with that last message, I thank you, and I can answer some questions. Thank you.
Thank you very much, Krista. Very entertaining and stimulating. I'm sure it will generate lots of questions, but we've only got a few minutes, so.
The question over there.
Thank you for the talk. I wanted to react to really the last point you made on the need for communication, because I very much agree with that. I, however, respectfully disagree with the point you were making that current LLMs actually support that. We as language engineers, we tend to, a lot of times, focus on the language. The language is just a means for communication. It isn't the thinking. It isn't really programming. It isn't the part in the middle. And when we look at dealing with simple programs like this, we miss that the real job is, for instance, something I actually worked on is how do you come up with a common model and an SOA architecture to federate 3 loan origination databases so you can run 5 billion transactions a year through it. To get from that statement, which was an English statement, to something actually running required multiple levels of analysis and design, which were not easily done in natural language, which required multiple artificial languages, modeling languages, representation languages, which we created and have created not just in computer science, but over 2,000 years, to do things natural language isn't good at. What I'm wondering is we have this powerful capability to do language machine learning now. Instead, we are focusing on the surface representation of large language models and how to, I would say, hack prompts in what is not a good way to communicate precisely, rather than, and you literally said, don't train the model, you can do it with the prompts. Well, why aren't we focusing on training the models with the kind of specialized domain data we need to handle large problems, rather than taking what are trained by somebody else to do other things and then trying to force them, like we would a person, into doing what we want?
Oh, I mean, so I think there are many points that you are making. The first, let me try to re-say what you said. So the first point is about that this is not just about little programs, it's about building systems and having sort of a shared understanding and a model of what's going on, and being able to understand systems at a larger scale. I completely agree with you. The other point that you are making, that you made also to the second part of what you were saying, is that there's these 2 ways of doing machine learning. One is to train models for specific problems with data that is specific to the problem. Another one is the large language models route, which is basically has been trained to understand natural language, and then from then on is able to reason and solve problems with reasoning. That is sort of and you know, I don't know, these are two different ways of going. The large language models, as far as I can tell, have been blowing the other more specific ones out of the water. Also because they have the capability to have fine-tuning. So if you have a data set that you really care about and you want to have things for that particular data set, you can fine-tune on top of this basically reasoning engine or language engine that is already pre-trained, right? And the other ones don't have that. So the other ones have only your data. So they are immediately more limited than the large language models. But you know what you were saying, I think that it relates sort of with this slide that I had hidden in the presentation. There's all things related to software construction. And I was talking just about the part of programming in a way. So, you know, getting somebody's fuzzy specification and putting it in square boxes. And there's lots of other things around. And I didn't, although I didn't focus on all those other things, my belief is that there are not the chatbot interface. Again, the chatbot interface is really misleading. I hope that's a point that I've been making here, that you understand. Chatbot interface is super misleading. There is, however, an opportunity for us and people working in this area to do applications that use LLMs for specific purposes, right? You don't put the chatbot interfacing directly with a person. What you do is you put the person, you decide what is the input of that person, and then you put some intelligent process under your control. Under your control, that's the important thing. That is repeatable, and it always behaves the way that you expect it to behave. So it's a little bit, it's more like programming in a way, right? But you're using the reasoning capabilities of these language models. So that's, I think, what I was trying to say.
Thank you. Perhaps if anybody's got a quick question, so we don't eat into the next. Okay, well, obviously a topic for great discussion. Thank you very much, Chris.
All right, thank you.
Now it works. Okay, took a while.
Okay, well, our second talk in this session is Nico Jensen from Aachen, who's going to talk to us about composing heterogeneous languages from the point of view of code generation.
Yeah, thank you very much. I'm Nico, and I want to talk about synchronizing the outputs of generators of heterogeneous modeling languages. So in general, what I'm talking about is the case of language aggregation. So what do I mean by this? Over the years, of course, there are several composition techniques of different modeling languages, and we can, for example, extend a language, we can embed one language inside another, and what we mean with language aggregation is that we have two completely separated modeling languages, and also their models stay in a separate way. So you see it every day if you open your browser. For example, look at a website, you normally have the HTML describing the content of a website and, well, maybe its structure, and then you have a CSS making everything looking nice. So this is exactly the same concept behind it, because you have two separate artifacts, or maybe even more artifacts. They're referencing each other and working to a common goal. And this is kind of the same mechanism which I'm talking about here with language aggregation. So here, for example, we have this automaton example where, well, a very small automaton, ping pong, with two states, ping and pong, and we have a transition from ping to pong, and we want to increase the number of strokes when we fire this transition. Now we see that this strokes variable is not defined in the scope of this automaton, but the automaton imports the corresponding class diagram. So what we're actually doing is we resolve for this name and try to find something which we can make use of. And this, of course, works because we have the symbol table structure, so we have a symbol resolution. We are looking for strokes with respect to the corresponding import statement, go outside of the artifact of the automaton, and go down again inside the artifact scope of the class diagram. Okay, this is what we mean by language aggregation. What I'm presenting next is how to actually do this with the back end of a language, because what I just presented is the front end of a language. You have your concrete syntax, you are able to parse it, you're checking for well-formedness, for example, whether the strokes variable actually exists, but you also have to do it at the back end, so when you generate code for it. What I'm showing you is based on the idea of the Monte Carlo language workbench, but generally it's applicable for other language workbenches as well. We have just the example that we have a pretty sophisticated symbol table infrastructure which exposes the interface directly to the developer. Therefore, it's easier to implement it there, but other language workbenches, for example, give an MPS or something like this, also have this symbol resolution, and you can implement it there as well. Okay, but now let's look at the actual problem, because here you have again a class diagram, an automaton, and the automata has a transition which can be fired if the age of the person, which is defined in the class diagram, is greater or equals 18 to grant some kind of access. Okay, when you're now processing these models and generate code out of it, you could have something like this. So above, you have simply, plain old Java generation. So you have your class person, you have the two attributes, name and age, and maybe some getter or setter functionality. And this is exactly the access you're striving for when you are generating code for the automata. So when you actually want to address the age attribute of the person instance, you have this p.getAge, so this getter access which you're referring to. And in this case, of course, this works fine. But it's not always that the class diagram generator generates the code like this. We could think of another scenario where we don't even have the class person which stores the age, but some kind of register with a static access map where you have this method search, which you can address by handing in some person instant and get the corresponding age back. This is, of course, an example constructed by me, but it's not out of the world that we can face something like that. So there's a complete different way of addressing this kind of code than that one. And if we just assume in our generator for the automaton that we have these getters available, we would have a compilation error when we are actually dealing with this register approach. So what we have to do is we have to adapt here. We have to have this register.search approach inside our if statement. And what we actually want to do is to adapt automatically. So as the generators might change and also the way how code is generated, we, as a generator developer of the automaton language, do not want to deal with these changes. We kind of want to have it working out of the box. So what we are actually doing here is we have the idea that, well, in the front end it works, right? So I just showed you we can resolve for this variable symbol and check whether its existence, and if it is there, we have actually the, well, rule of thumb that our model is well formed. The idea is to use exactly the same approach for composing the generated artifacts. So just using the symbol table, enriching it with further information of the generated artifacts, and simply resolving for the symbols, addressing this attached information, and extracting the information for our own generation process. So what we did is we extended this symbol table infrastructure by augmenting it with a generator information, which then again stores templates of the target code. So we also strived for a pretty, let's say, lightweight interface, because we are not the first ones who are doing this, of course. But it turned out that approaches that are not hard-coded tend to be a little bit clumsy. So you might have some kind of big interface which you have to implement against to make the generators work together. But often it turned out that well, adhering to the interface was complicated enough that a generator developer said, okay, I can simply hard-code it that it works for the other generator as well. And this is, of course, something we don't want. So we strived for a lightweight contract between the generators, and our idea was to just use CRUD operations as this kind of contract, to have these create, read, update, and delete operations as the interface between the generators, but nothing more, or I should say, not much more than that. And regarding these operations, you can simply address, as I just explained, the corresponding access templates and extract the code how to address or access the corresponding generated elements. Here, maybe we have a look at the instance side. So let's assume again our class diagram with the single class person and the attributes name and age. And then we have the, we pass this model, we construct a symbol table, which is represented here as an object diagram. It's a little bit simplified. I omitted the scope structure just to give you an expression. We have the type symbol, person, which has two field symbols, name and age. Okay, nothing fancy about that, but now we have, of course, this augmented generator info, which provides operations for read and update, so exactly for getting and setting the age attribute. And this is actually all there's required to enable the providing generator with the information of the access for the corresponding symbols. So if we have a look at the templates, it's actually pretty easy. So first we have some kind of context. If you recall, the age attribute wasn't standing alone there, but we had this attribute in the context of the class person, so actually the instance of the class, but I'm omitting that here. We simply get the name of it, and then start with this getter access, followed by the name of the symbol, in this case age. So in fact, we would get, well, the name of the context. In our case, it was p.getAge. Also a little bit simplified because you have to get a proper getter, you would have to capitalize the A of the corresponding symbol, but it's just a little bit more of boilerplate. Okay, and the same holds, of course, for the setter of the corresponding value. And if you want to change it, for example, with the scenario B, where we had this register, it would simply look like this. So here we are completely omitting the symbol itself because everything is provided by the register. We have this search method and simply have to give the instance P, so the context inside it. Okay, and this is the main idea of what we are doing here. so that our new generator tool would look something like this in a very abstract way, to be honest. So up there we have the normal things we're doing. So we start with the model, parse it, we have the AST, maybe build up the symbol table, throw everything in our generator engine. In our case, it's a template engine, so this approach is a little bit, well, forced, not forced, but focused around templates. Yeah, you start generating the code, and always, if you don't know how to address some symbol which is not stored within your own model, you consolidate such a composition printer which simply resolves the symbol and asks the symbol for the corresponding access template, which is then handed again forward to the template engine. For us in Monticore, it's explicitly easy because we have this functionality of storing and loading symbol tables. So we don't have to reprocess models again and again. We simply store a symbol table once a model is processed out there in a kind of JSON format, which is parsable pretty efficiently, and then we can load it, and we can also store the corresponding access information there. So there it's pretty easy to just go for, yeah, processing it once, augmenting it with the corresponding template snippets, and storing it, and then the other tool can just parse this JSON again, has the symbol table available, and can address all the symbols. Okay, to have a slight insight into what's actually going on internally, we go back to our example from the beginning and try to recapitulate what's actually happening there. So imagine we are at the transition where we want to check whether the person has the correct age. As you remember, we had this translation to the if statement, and inside the if statement we had the expression where it gets interesting. So this is overall what we have inside our generator. We have this template engine, the already instantiated composition printer, and, well, some surrogate for the overall symbol table which we can address. So now, as we are at the expression, we simply ask the printer to print this corresponding expression, which then starts resolving all the symbols involved inside this fully qualified name, because we actually need all of them in a single manner, because they are later dealing towards the context. Okay, so first we resolve for p, because the expression was p.h. Of course, we find it as we can load the symbol table, so there we have the variable symbol person. We return it to the composition printer, which then goes forward resolving the h attribute. So again, we simply resolve it. It's now available. Okay, now, as every symbol is resolved, we go forward in actually asking the h symbol how to generate the code to access it. So we ask the h symbol, yeah, how can I read the corresponding symbol? The composition printer, as it knows the expression, because the expression is defined within the realm of the automaton language, knows that this is a read operation. So we only have to ask the variable symbol, okay, how can I read you with respect to the generated code? And then the variable symbol simply hands back the corresponding template, which is exactly the same which we have seen before. So the template is just handed back to the template engine, which processes the value with respect to the corresponding context person, and then it's just executing this template. So first, we ask the context for the name. The context was the person symbol. Yeah, it's P. Then we ask the symbol itself for its name. It's H. We put this together with respect to the rules of the corresponding template, and finally can return the whole string p.getH, again omitted that the A has to be capitalized. Okay, and as a last step, the composition printer, as it wants to print the whole expression, just adds this greater or equals 18, and we are done. Or not really done, because there are plenty of other calls to follow, because this was only the translation of this pretty small snippet, of course. But this is actually all there is about to realize this concept. And we already tried it in a demonstrator for a test data generator. So on the left-hand side, you see an object diagram for, well, instantiating test data. In this case, well, we have a user Alice and a user Bob with separate usernames, password, emails, and a role. And what the original generator actually does is it generates a instantiator class for the corresponding objects defined inside the object diagrams for, well, instantiating them and then using them inside of a JUnit test or something like that. And if you don't know about the target, you of course have a problem because you want to instantiate the values corresponding to whatever your target code is. So if you don't know anything, you could assume some plain old Java. Here again, you would have some kind of constructor and then just use setters if available for setting username, password, and so on. But normally you have systems which are a little bit more complicated than that. For example, think of an online shop. There it would make sense to have these users. And there could be a kind of shop manager which provides the actual builders for the object, which then can be called in the normal builder fashion to set the corresponding values. And this is what we actually tried to have these two different cases where we actually can adaptively switch just because of whatever the class diagram generator generates. So class diagram described the data structure which was behind this, of course. Okay, so this is what we actually did and what we tested here. Maybe some words towards open challenges and potential future work, because yeah, this is in a very early stage. So we just decided for CRUD because it's first pretty lightweight and most people simply know it. It's not hard to learn. But you of course have to ask whether CRUD is always the best solution. And there are of course different symbol kinds which are not directly mappable to the CRUD operation. So I have simply brought some examples for a type symbol, a variable symbol, and a function symbol. So symbols we pretty much know also from programming. And here we see that in some cases, not all of them are really applicable. So there might be cases where we don't have a template for the corresponding CRUD operation. We even saw that in the example before, where we could provide read and update operations for the variable, but didn't care about creation or deletion. This, in fact, is not that much of an issue, but of course we have to be aware that there can be holes in our interface. The other way around is a little bit more critical because maybe CRUD simply isn't enough. And on the left-hand side, I've brought an example for, well, translating an automata. We could use, for example, the state design pattern. And when we use that, we of course have classes for the corresponding states. This is only the case with respect to that pattern. Otherwise, we can, well, simply store the case in some kind of integer or enumeration. So just by using this pattern, we have some newly accessible object inside our generated code, which is not really visible from the model side. This simply has to be investigated more. Hopefully the answer is simply, yeah, maybe we have this generation type, but we don't care because from the outside we never want to look at it. But to actually have an answer for that, we have to investigate the symbol kinds which are out there and have an, well, assessment what are actually the information you want to access from them and which are not. Another case where we already have found a limitation is with respect the translation itself. So you remember the strokes increment from the example from the first slide. Here I simply made it a little bit shorter using an S. Maybe we have a guard and we want to check that the increment of S is equals 3 and then again the increment, but using the other operator then, is equals 5. I don't want to put such expressions, but it's totally possible. So then, again, we would have directly a problem if our target language, which we are generating for, does not support such operators. But okay, let's assume we can support these operators, but even then we have a problem. Let's assume we are generating Java code out of it. As these are on-the-fly increments, we have the issue that if the variable is defined outside, as we had this in our example for the class diagram, we would normally don't access it via the actual attributes, but at least via a getter or something like this. And then we don't have pointers towards the real object because these are primitive data types. And we cannot directly do the increment inside our if statement. And this is an issue where we need auxiliary variables, which is currently not inside our concept, but definitely something we have to look at. Because, yeah, first I have to do the increment, store them into some auxiliary variables, and check against them here in the if statement. And this is a particular problem because from a generator point of view for the automaton, when you have to do this, you're already here, right? So you started printing the if, the bracket here, then you simply say, okay, printer, let's print this expression. And the printer says, yeah, okay, but there is something I have to do before. So we are actually influencing the control flow of the generator. And this is something we have to look into to make this also in a pretty light way and fluent way possible. And if you looked in detail, you see that I even cheated here a little bit because I just translated these two sub-expressions without any connections. But in order to execute sub-expression B, which I have done here, I would actually have to check whether A was successful. Otherwise, I cannot execute it. But these are details I just omitted for the presentation purpose. But this even shows that it's more complicated than this, because this would result in another if statement just influencing the control flow of the generator. So yeah, there is definitely still some work to do. And this already brings me to the end of the presentation. So in fact, we conceived an extension for the symbol table infrastructure by augmenting it with corresponding accessor templates based on CRUD operations. We definitely have to do some further look into what actually is generated there and what else do we need to, well, in a lightweight fashion, influence the control flow of the targeting generator. Yeah, thank you very much. I'm open for questions.
Thank you, Nico. Questions?
Thanks. So this lets you sort of be able to read and update symbols sort of across languages by having a sort of universal symbol table or some symbol table that both languages understand. What happens sort of next when you want to translate and run these things, right? That if one language translates to Java, the other one is interpreted in Python, it seems that it's a totally different story. So your aggregation claim is that they're still kind of closely related languages, that they're translating, they have the same runtime in some sense, right? That they're not really that different. They're different on a syntactic level, maybe, but at least the runtimes have to be common.
Yeah, so you're absolutely correct there. I only conceived the same target language. So this wouldn't work for different languages. Well, it could work. You could have some kind of, but then it gets more complicated, contract that you're kind of communicating via a REST API or something like that. But let's ignore that fact. Currently, if you would have Python and Java, you could not really couple them. As you said, they are similar in nature, so maybe we can also find a solution there, but the main idea behind this concept was it's the same target language. Thank you.
Yeah.
It's well pronounced?
Yeah,
Right?
yeah, yeah, correct. Yeah.
So
This is
Correct.
your presentation, right?
Yeah.
The only thing I'm going to ask you is when you put your computer, you need to plug two cables. Do you have any video with audio?
No.
No? Okay, so only two cables, HDMI and the pointer, that it's going to be on the podium.
Okay.
So you change slides here.
I have my own pointer.
You
Can
want
I
to use your
yeah,
own?
Yeah.
Okay, perfect.
Yeah.
So only one cable.
So yeah, only one
cable,
right.
HDMI.
I can.
If you need, I'll be here in front. If you need anything, I'll help you.
Good.
Okay?
That's good. I think it works.
Yeah. This hub is yours.
Oh yes, this is mine. Thank you.
Thank you. Do you have any sound in it or videos?
No.
No? Okay. And do you want to use the podium microphone for the presentation?
Yes.
Try always to speak to the microphone because we're live streaming and we need the sound constantly.
Okay.
If you want, I can leave you a hand mic here.
No, it's okay.
Okay. It's going to be on when you start the presentation.
So
do you
let's
want to
check.
use this for your slide?
No, I will use
You prefer
this.
to use your laptop
Yes.
directly?
Yes.
Yeah, okay.
Okay, you just need to connect the HDMI. You can push it. You can take it. Do we have any filters?
Yes.
And for this part after lunch, it's probably great. You do only per session, two presentation.
No, three.
Three?
Yeah.
Okay.
So here's the first one, here's the second one, and we are still waiting for the summer.
Okay. So as soon as the third one arrives,
Yeah.
because sometimes we want headsets and we put it before
Okay.
the presentation. Okay.
As soon as I
If you
can
can
see.
help me
Yeah.
doing that part because I don't know.
Sure,
Okay.
sure, of course. Thank you to you. Thank you for your help.
Cool.
Excellent. So we take probably 3-4 minutes.
Okay,
Yeah.
that's fine.
That's green because they wanted to. That's why I put this one. But you can put it here. So this is the problem. This is the preview that I choose.
Okay, so it's probably time to start this afternoon. Welcome everyone to this session of SLE. So the session is entitled Modeling, whatever modeling means in that context. We have 3 exciting presentations during this session, 3 research papers that will be presented. The first one will be about blended modeling, and I think we will discuss about textual and graphical notations. The second one will be about model comparison, and the third one will be about heterogeneous modeling versus viewpoint. So it's going to be a very exciting session, so please feel free to follow the talks and to ask all the questions. We will take a few minutes at the end of each talk for having a Q&A part. And that's it. This being said, I think we can start with the first presentation. The presentation will be given by Muhammad. And the title is Enabling Blended Modeling of Timing and Variability in East ADL. So please, Muhammad, the floor is yours.
Okay, thank you. So good afternoon. I am Mohammad Wasim Anwar, and I am going to present our research work titled Enabling Blended Modeling of Timing and Variability in East ADL. This work is supported through Bumble and Modave projects. So this is the presentation outline. I will start with the background of this research, followed by the problem statement. Then I will discuss few state-of-the-art approaches. Then I will explain the proposed blended modeling framework, followed by the proof of the concept implementation. And finally, I will conclude the presentation with future directions. So what is blended modeling? So the concept of blended modeling was first introduced by Sekozy et al. As the activity of interacting seamlessly with a single model, referred as abstract syntax, through multiple notations, concrete syntaxes allow a certain degree of temporary inconsistency. So the runtime synchronization between graphical and textual notation is a key characteristic of blended modeling. Blended modeling aims at boosting the development of complex systems by enabling seamless multi-notation modeling. So experiments have shown that blended modeling has the potential to maximize the throughput of stakeholders involved in the modeling activities. EastADL is a domain-specific modeling language for automotive embedded system. It is based on the 4 levels of abstractions: vehicle, analysis, design, and implementation. So at vehicle level, technical feature model are developed. And at analysis level, different concepts like analysis functions are available for the modeling of analysis features. So this allows to perform the early analysis on the system model. The design level is divided into 2 further components: functional design architecture and hardware design architecture. So functional level design is developed through the FTA, and hardware-related concepts are modeled through the HTA. Finally, the implementation level is dedicated to the other languages like AutoSAR and RCM. In addition to these levels, there are other packages in EastADL like requirement, dependability, variability, and so on. So these packages can be applied at any of these levels as shown here. For instance, the timing constraints can be annotated in the system model through the timing package. So this is the overall architecture of the EastADL. So on top of EastADL architecture, several tools have been developed supporting tree-based diagrammatic modeling for automotive embedded system. For instance, EATOP, MetaEdit Plus, Robust, these are few to name. The interoperability among various EastADL tools is achieved through eXML. It is an XML-based exchange format that represents the serialized form of the EastADL meta model instances. So what is the problem we are going to solve? So currently, EastADL tools traditionally focus on the diagrammatic notation rather than the textual one. So this limits communication across different stakeholders. And it is not possible to create models that do not fully conform to the meta model to ensure rapid prototyping and evolution of contents. So such issues severely affect the productivity and time to market objectives in automotive domain. So to address these issues, blended modeling environment for EastADL is desirable to support both textual and diagrammatic notation for system modeling. facilitate the runtime synchronization between notations, and provide the tool-independent implementation to work with the existing EastADL tools broadly. So the notation of blended modeling may seem similar to or overlapping with multi-view modelings. So multi-view modeling basically based on the viewpoints that can be composed of one or two models, while blended modeling focuses on the provision of multiple concrete sentences for a single abstract syntax. So the runtime synchronization between concrete syntaxes with temporary inconsistency is a key in the blended modeling. So blended modeling has been explored from different perspectives in industrial settings. This can be broadly categorized into two classes, UML-based DSML and meta models. So for instance, in 7, author applied the blended modeling to HCL artist environment to support the modeling of state machines through graphical and textual notations interchangeably. In 8, author applied the blended modeling to Ericsson Hive DSML. So this shows the effectiveness of blended modeling in industrial settings. So EastADL was introduced in 2004 under the East EA project. Since then, several aspects at different levels of abstractions have been investigated and evolved. So there is a long list of areas that have been investigated. I am just highlighting the few important areas like the verification and analysis of timing constraints have been frequently researched. Similarly, safety aspects in line with the ISO 26262 standards have also been frequently researched. So it is evident from the state of the art that the blended modeling offers enhanced modeling flexibility to boost collaboration, lower modeling time, and maximize the productivity. In addition to this, EastADL has been explored in different areas like timing analysis and safety. But the blended modeling support for EastADL has not been targeted yet to the best of our knowledge. So to get the benefits of the blended modeling in automotive domain, in this research work, our goal together with our industrial partner Volvo is to provide blended modeling features for EastADL. So now I'm going to explain the proposed framework. So this is the current situation. Based on the EastADL architecture, several tool chains have been developed like EA Top Robust that support the graphical editors. So the system modeling can be developed using different modeling entities using different packages like variability, timing, and so on. So this model are represented in eXML to support the interoperability among graphical tools. So for the provision of the textual notations, we exploit the XText framework where the first step is to define the XText grammar for EastADL packages of choice. This can be structure, variability, timing, and so on. So this leads to a textual editor supporting the modeling in textual notations. In the second step, deserialization and information extraction has been performed using the eXML from the graphical editor. So at this step, the different entities from the graphical editor have been extracted. So, the extracted information from the graphical editor cannot be directly propagated to the textual editor due to the syntactical differences between the graphical and textual notations. So for this, at step 3, transformation need to be implemented for the seamless change propagation from the graphical editor to the textual editor. So at this point, the changes from the graphical editor are propagated to the textual editor. At the step 4, transformation need to be implemented to convert the textual instant model into the eXML format. This is essential for the change propagation from the textual editor to the graphical editor. So at step 5, serialization is performed as most of the graphical tools only operate on the serialized eXML. So this leads to the updated eXML, and in this way, the changes from the textual editor are propagated back to the graphical editor. So in this way, the step 2, 3, 4, 5 are executed iteratively to achieve the blended modeling in each ADL. So for proof of concept, we select two East ADL packages, timing and variability. This selection is based on the industry partner recommendation. Then the selection of syntax for textual notation is equally important. For this, we propose two options to industry partner. First one is the natural language-like syntax, and second is the programming language-like syntax. The team at Volvo prefer the programming language-like syntax because the engineers and developers are more comfortable with this. So we use EA-top modeling workbench for proof of concept. It is the de facto development environment at Volvo. And finally, we use the car wiper case study for demonstration. So this is the interface of the EA-top here. System modeling can be done using different East ADL package. This is the car wiper model, and this can be represented in EXML. Here, EXML serves as a synchronization point. So we implemented the timing and variability X-text grammars, and as we already discussed, this allows us the two editors to support the modeling in textual notations. So we implement the step 2 deserialization and information extraction in Java in XML DOM. And for the change propagation from graphical or EA-top to textual editor is done using the Java. And we implement the EXML transformations in Extend and Java to convert the textual model into EXML. And finally, we perform the serialization in Java. So this lead to the propagate the changes from the textual editor to the EA-top. So this way, the real-time synchronization between EA-top and textual editor has been done. So this is the East ADL timing meta model. Here you can see timing is the main concept that contains the other concept like timing, description, and timing constraints. These concepts are further divided into different other concepts. For instance, the timing constraints allow the modeling of 20 constraints. So this is the modeling concept of East ADL variability package. Here, variability is the main concept that contains the other concept for the modeling of the product variants. So this is the X-text timing grammar that we have implemented. We defined different East ADL timing concepts. And in the X-text grammars, our objective is to provide the syntactical sugar with temporary inconsistencies for textual notations while preserving the semantics of the meta model. So this is X-text variability grammar, snapshot of the X-text variability grammar. Here you can see different concept, definition of different concepts have been provided. So this is the X-text editor for timing. And here you can see the user can specify different timing concepts through a programming language like syntax, like event functions, constraints. We have currently defined around 10 constraints in this. So this is the text editor for variability. So this is the snapshot of the EXML transformation that convert the textual instant model into the EXML for change propagation from textual editor to the graphical editor. So blended modeling in practice. Now I will explain the actual application of the proposed approach in the industrial setting. Here you can see the model of a car wiper. It is basically the design of the car wiper using different design level entities like design function, prototype, functional correctors, and so on. Please note here, the variability and timing related modeling is not available at the moment. So here you can see the textual editor where user can specify the timing related information in programming language like syntax. Here you can see that all the information from the EA top is available in the textual editor. Like all the design function prototypes and other information is available here. So in the textual modeling, one can use this information. So here you can see the timings we defined in the textual editor are now available in the EA top. So this way, the runtime synchronization works. That things we define in the textual editor are available here, and the things we define here are available in the textual editor. For instance, here we define another event function blended. So you can see it is immediately available in the text editor. So the proof of concept implementation, case study model, user manual, and video demos are publicly available at GitHub. So you can further explore this. So in this work, we report on our language engineering work toward the provision of blended modeling for each ADL to support seamless graphical and textual notations. So this significantly boosts collaboration and lowers development time, eventually improving the overall productivity. So this research can be extended in multiple directions. For instance, one probable direction is the extension of the current approach for other East ADL packages like structure, variability, and dependability. Another important aspect is the change propagation time between the notations or editors, because this is really important while dealing with the large models. So in this work, we performed the initial evaluation on the change propagation time between the editors. But more comprehensive evaluation is required. So in this context, we are working on the break-by-wire case study to provide to analyze this in broader context and to optimize it where needed. So, thank you.
Thank you very much. So we have some time for a few questions, and we'll have some help for circulating the mic. So yeah, please head.
Thank you. It's a very important topic, actually. But trying to follow what you have done and what was future work, but I didn't actually see any graphical notation in your graphical editor. You just had the outline. One of the issues is always doing the synchronization is how you deal with the layout when you change things. Is that addressed at all? Did you just not show that, or did you say that you haven't gotten to that?
Your question. Basically, the EA top is here. We represent the EA top as a tree editor. You know, we have the plugin for the graphical. These are converted into the graphical notation. The point is, we are basically using the meta models and the abstract syntax. So, and this is also based on the abstract syntax.
The tree editor is easier than dealing with the actual graphics. So that's a key area.
Yes,
there.
yes.
One other thing related to that, and then I'll hand it off for them. Oh, go ahead.
We were working for the same project, and the company Volvo developed a graphical viewer. They can see the graphical model, but in that graphical viewer, the models cannot be edited. It's just a viewer.
Okay, so you would relay it out.
Yeah.
So you revisualize it. Once you update it, you just revisualize it each time.
You
okay, you can't edit. That makes it easier. That also, do you try to maintain the identity when you go to from the meta model view, where each of these elements has a specific identity, to the text and back again? Can you maintain the identity of elements?
Yes. Yeah. Yes. I think the idea is that they have already have a tree-based syntax and they also have the graphical syntax. They both adhere to the meta model, and now they use the same meta model to generate a textual syntax. So the textual syntax is also adhere to the same one meta model, and the models in different notations can interact with each other.
Can you use the mic? Yeah, because we are live streaming, so that's why we try to keep the mic.
The question was on how you do the incremental update without reparsing everything, but I'll follow up afterwards. Thanks.
I think there was another question, Andreas.
So thank you for the talk. I'm wondering if you wanted to translate what you have learned and done for EastADL to another popular architecture description language such as AADL or MontyArc, what would you have to do?
Sorry, please repeat the question.
How can I translate your results to another architecture description language?
I think the question is how you can generalize what you did for EastADL for another language, and more specifically for another architecture description language.
I have no idea about the architecture you are talking
Okay, might be future work. Thank you.
Thank you.
I guess it would seem like any language you could express in X text with an underlying meta model, you could use this same approach. I mean, you could use it in other technologies, but you'd need a parser and
Yeah, but it's not generic, right?
The mic, can you use the mic, Andreas?
So thank you, Ed. But I think this is not generic. So there are some parts that might be specific to EastADL and some parts that seem to be generic. And I try to understand exactly.
the steps looked pretty generic if you had each of these pieces and an underlying XML representation.
I think there are some technologies that can be generic to other languages. We had a paper before to talk about how to extend the X-text generator's capability and and also its implementation. So that technology has been described in that paper, and it can be used in other languages. And here I also want to ask the author, because we were working in the same project, and we developed a textual language for EastADL as well. And we have also have a working paper for the blended modeling on EastADL. I'm very surprised you also write this paper. I remember that you were working in another language called Artist. So it's I think you should let us know, I think. Yeah, because we have we share the code. You can see our code. So I'm. Yeah.
Thank you very much. Is that there is another question just there.
Thank you for your talk. My question is related to EXML transformations. So you mentioned you use Java. Is there any particular reason you use Java and not any transformation language?
Basically, we use extend, and this can be done through the model-to-model transformation as well. But in this case, we have to provide some temporary inconsistency in the textual grammar. Because we need to propagate the result of the verification back to the model. So for this reason, EXML is more suitable for us.
Nice, thank you.
Is there any last question to Muhammad? Okay, I will have a few seconds for asking you my question. So you discussed about how to combine textual and graphical modeling, but my question was more about which part should be textual and which part should be graphical, and which textual and graphical syntaxes future users are expecting. So my question is, how did you involve the future user of this language in order to define what should be graphical, what should be textual, and for each part, what should be the keyword, for example, for the textual one, and what should be the graphics for the graphical one? How did you engage the future users?
Tool is already available here, EA-Top. So in EA-Top, you can develop the tree-based modeling, and you can visualize it as a graphical model. While in the X-text grammar, so we provide the textual syntaxes. Most of those are equivalent to these graphical notations. But there are a few temporary inconsistencies. There are few additional elements in the X-text grammars. So that we will use in different other contexts, like the propagation of timing constraints, verification result back to the models. So this is not suitable using the graphical notation, because for this reason we have to update whole meta models.
Okay, so that's for the choice of the graphical versus the textual one. And then for the choice of the different keyword, for example, in your grammar. So in the X-text grammar, you have chosen some keywords.
Yes.
You have chosen a programming language style, as you said. Yes. Everything has been chosen by involving the future users, or is it choice that you made by own?
Of course, the Volvo team was involved, and they recommend. I already told we proposed two syntaxes, like natural language syntax and the programming language. So the team at Volvo were involved about this. Okay. And it is based on their recommendation.
Super. Thank you very much.
Thank you.
So I think we can thank again Muhammad for the presentation and the answer of the question. Thank you very much. Please. And now. Super. So, whenever you want, Korat, the floor is yours. Thank you very much.
Thank you. Good afternoon, everyone. I'm Kuratulene Ali from University of York, and today I'm going to present our work on efficient model comparison using automated program rewriting. This work is done in collaboration with my supervisors, Professor Dimitris Kolovos and Konstantinos Barmpis. So today I'm going to start with introduction, so a little bit about a few terms that I would be using during this presentation. Then I'll touch upon the tools and technologies involved in the context of this research, which is Epsilon, and in particular ECL, Epsilon's comparison language. I'll talk a bit about the problem statement and the motivation behind this work. Then I'll talk you to the proposed approach step by step. And finally, I'll share some results of our approach, and I'll conclude with a summary and some future directions for our work. So because models, I know this is a session on modeling, but models can be used in the machine learning terms as well. So I just thought to give a brief overview of what I mean by models here is, so models are basically an abstraction of a real-world system, which is for a given purpose. And then in model-driven engineering, models are the first-class citizens, so they are the primary artifacts from which we generate other software artifacts. So we have various model management languages to do various model management tasks. So we can actually generate code, transform models, compare them, merge them, etc. So in the context of this talk, we are focusing on model comparison. So I'll just say a few words about what model comparison means. So model comparison means to establish the correspondences between two models that you're comparing. And model comparison is usually a prerequisite for other model management activities, such as model differencing. So if you want to calculate the difference between two models, it is important to identify the matching pairs. Similarly, for merging, to not have duplicates in the merged models, it's important that you identify the corresponding matching elements. So now we know what is model comparison. What are the ways to compare models? So traditionally, we can use the traditional text-based comparison or unique identifiers. These are simpler, but they provide limited support, and they cannot be applied to heterogeneous models. So we have a dedicated rule-based language, which is Epsilon's comparison language, that allows you to have a precise matching algorithm that can be specified by the developer to have a custom matching logic. So just a depiction of what model comparison looks like. So if you see, we have a object-oriented model, a relational model. So we put these two as an input, and they correspond to their corresponding meta model. And then the model comparison task will yield a match trace. And what is a match trace? It's nothing but a table that looks like this. So we have a left elements, like this one, and we have right elements, and then we have a Boolean flag that basically shows if these elements match or not. So before I go to ECL, I think it's important that I say a few words about Epsilon. So Epsilon is a family of model management languages, and it provides an abstraction to different modeling technologies using this model connectivity layer, where you can access different models, and then you can use any of the language depending on the task that you're targeting. So the main thing to take from here is that Epsilon's main core language is EOL, Epsilon's object language, and all the other languages are built on the top of it. So the language of interest here is ECL, which is used for model comparison, as I mentioned. Now, before I go to proposed approach, like how ECL looks like. So ECL is, as I mentioned before, is a rule-based model comparison language. We can compare two models from the same modeling technology or from different. And then an ECL program looks like this. So if you see, we have a rule here saying tree to tree. Basically, what this rule is doing is comparing two tree models conforming to this meta model. We have a keyword match that specifies one model element and then the other model element to compare it with. So L is a model T1, and then R is a model T2. And then what we do is we have a compare block which specifies the matching logic. So what's happening here is we're checking if the label of tree is similar, and the parent of the left tree is the same as the parent of the right tree, and also the same for the children. The important thing here is this matches operation, because this is just an equal operation. This matches operation is basically a built-in operation that ECL provides, and this is basically used to avoid duplicates. So basically, this provides decoupling of rules. So for instance, this matches operation calculates the model elements compared by the other rules. In this case, there is just one rule, so this matches will call the same rule again. So this is what ECL looks like, and ECL also has can have pre and post blocks. So pre blocks will be statements executed before the match rules, and post block will have statements to be executed after the match rules. The output of an ECL program is a match trace, which contains several matches of left, right, and a Boolean flag. Right? So now we've seen what ECL looks like. The problem here is that when we are in an industrial setting, or we are dealing with enterprise applications, the size of models is usually quite big, so we have models ranging from millions of elements. So we need to make them scalable to make more efficient use of the resources, right? So as I mentioned, these languages like ECL, they are tailored model management languages. So they are specific to the task that they are targeting. They're simpler to use, but because they are interpreted, most of the time performance becomes an issue. So especially in model comparison, where we have to traverse every element and compare it to the corresponding element of the other model. So I think a motivating example will help understand better what I mean by this. So for instance, we have a sequence diagram here, a meta model of a sequence diagram, a meta model of class diagram here. And suppose we want to compare models conforming to these two meta models. So we have an ECL program written here, a very simple one. We're comparing message to operation. So we're checking if the message and operation name are same, and they belong to the same class, right? And then we're comparing lifeline to classes. But if we want to evaluate this on these small models, so this is a small class diagram, a small sequence diagram, the match trace that we will end up with would be this. It's a huge match trace for just some small models. So imagine if we are considering the underlying models to be in order of millions of elements, then we'll end up with a huge match trace, which will decrease the performance of ECL engine. So the idea is to optimize the ECL program so that we can end up with a filtered or reduced match trace, right? So the approach that we have proposed for this is illustrated here. I will go through this step by step, but the main idea is this, that we have a ECL comparison script here that is comparing a left and the right model conforming to their respective meta models. And then we have a static analyzer block that takes in the abstract syntax tree. Here we have a, if you remember the diagram that I showed you earlier about epsilon, because ECL extends EOL, so the static analyzer also extends the static analyzer of EOL. So what will end up from the static analyzer block is a type-resolved AST, which would be the same AST as we've seen here, but with the type information attached to it. Then we would use a dependency graph generator that would generate a graph that will depict the dependencies between various match rules. And then that would help us for the scheduling of rules. In parallel, we have a optimizable rule detector, so we'll detect which rules we can optimize. And then there is a rewriter that rewrites the whole comparison program. So now this comparison script is reduced to this rewritten comparison, and this will be executed on the ECL, the traditional ECL engine that is available. And what we'll end up with is a reduced pre-filtered match trace. So that's the whole idea. Now we'll just look at each block one by one. So the static analyzer block. So the same program that I've shown you in the motivating example. So what we do here is static analyzer basically computes types of the various constructs. So as an example, the L variable here, because the type is specified to be a message type, which is a EOL model element. And then we would have the same with the operation. It's a model element type, so on and so forth. And suppose for the primitive types, r.name, as shown from the meta model, is a string type. So this is what static analyzer does. So now we have an AST, which has all the type information attached to it. So in the second phase, where we have a dependency graph generator, what happens is these matches operation, basically this matches operation has means that it is dependent on another rule. So the resultant of match flag of the other rules needs to be attached here. So what we do is we compute based on the types that we've resolved from the static analysis. We see which rules are dependent on which. So for instance, if you see L dot 2 here, 2 is a type of lifeline from message. And then R dot class is a type of class here. And then we know that this is calling a rule lifeline to class, any rule that is comparing lifeline with class. So the dependency graph would end up like this. So we'll know that message to operation rule is dependent on lifeline to class rule. So that's what dependency graph generator does. In the second bit, we have a rule scheduler. So rule scheduler takes in the input from the dependency graph generator and schedule the rule accordingly. So for instance, here, this lifeline to class rule is independent, and message to operation rule is dependent on this rule. So the rewritten program would put the second rule at the top and the message to operation one below it, because when we would ask for this matches operation, the result would also be would already be calculated by this rule, right? So the idea is to use the input of the dependency graph and use it to schedule the rules. Now we will come to the second part, which is the detection of optimizable rules. So here what we do is we basically find out expressions like this. So expressions where we are comparing using an equal operator. So now we know that we only need to compare those lifeline to classes where the name is similar. So what it currently what it will do is it will compare all the lifelines with all the classes. But if we know this beforehand, we can index this, right? So before going forward, so from after this step, what we will end up with is the rule and this, this field from which we need to create an index. So the second step in the rewriting phase is injecting caches. So I mentioned about the pre-block usage in the epsilon's comparison language. So we have a map by built-in operation provided by EOL. So what we do is we are creating an index based on the name field. Why we're creating it on the name field? Because we're comparing the name field with each other here. So now we've created an index. We need to rewrite the program. So this program, if you see this program, it will be rewritten to this. Now there is this thing, which is different. So what we are doing is we are creating a concept of domain. So we've extended ECL to include this keyword from. It will filter this R array, and it will just compare the ones which have the same name. So L.type would return the name of the lifeline, and then this class map is a index that we've generated here. So in the compare block, we're just writing true. So it will only compare the lifelines with the classes. So this is a simple example of the rewritten script. And then when we execute this script over the ECL engine, what will happen is we will end up with this match trace. So if you see, this match trace is much more smaller than this huge match trace that we ended up without an optimization algorithm behind the ECL script. So this is the proposed approach. Now we evaluated our approach with the two types of models, so class and sequence diagram models that we mined from GitHub, and then synthetic models of object-oriented and DB. And then because we are rewriting the program, it's very, very important to ensure that the program is still correct. It produces the same output as it should be producing before the optimization. So We did it using the equivalence testing. I'll talk a bit about it in the next slides. And then, like to compare our results, we use the traditional ECL engine, which is the one that ECL normally does. And then we have rewritten the script using the optimization algorithm that I just showed you, and then executed it using the same ECL engine to see the comparison between the results. So here, the graph that you can see is a graph comparing class and sequence diagram models. So this blue line is for the traditional ECL, and this red line shows the optimized ECL. And you can see there is a huge difference in the execution time. Obviously, it comes at the cost of memory because we are storing a cache. And then same for the OO to DB example. The red line depicts the optimized ECL, and this one is the traditional ECL engine. This is the table that depicts the number of model elements that we've evaluated our approach on. So just the final bit about evaluation is here it's the equivalence testing that I was talking about. So we have, these are the number of matches basically. So we have number of all matches in ECL and number of all matches in optimized ECL. And then we have number of successful matches in ECL and then the optimized version. So what you can see here is that the successful matches number still remains the same, which is what we expect. But the all matches are reduced because now we are comparing a pre-filtered domain. So same goes for the class sequence diagram model. To conclude, I've talked about an approach which optimizes a model comparison program using three main techniques: static analysis on the top of it, and then dependency graph, and then program rewriting. So we have experiments that deliver significant performance improvements in terms of execution time. So this is what it can do currently. This rule-based, because EPL is another epsilon-based language, epsilon pattern language, so these optimizations, like the dynamic domain concept, can also be integrated with other EPL language, and also we can include more experiments to show comparison between different modeling languages, like Simulink and repository-based models. So in paper, you can find more details on the running example, and also you can find algorithm, how we identify optimizable rules and how we do the rewriting. That's it from my side. Thank you very much, and I'm open to any questions.
Thank you very much for the presentation. So is there any questions? We have many time for questions. Yeah, please.
Hello, thanks for a nice talk. So I was wondering, the result that you get is a match trace between matching objects. So is it trivial to produce a diff from this match trace and the original models? Or is that, would that be complex?
Sorry, can you repeat, is it trivial too?
So if I would like a diff between the models, is that easy to get from the match trace?
Right. So if you want to have a diff match, like matching is the first thing that you would do, like to identify which elements are matched. And then differencing is the second task that you would do on the top of it. Now you know which elements are matched. And these matches, remember, because these are on a custom matching level algorithm, so it depends what matching algorithm you write yourself using ECL, right? And then you would calculate a difference, because now you know that which elements correspond to each other according to your comparison language, logic. Yeah.
Okay, thank you.
Any other question? Yeah, Nico.
Yeah, also thank you for your talk from my side. I have one question regarding the optimization. Did you face some kind of rules which were, let's say, hard to optimize, where you couldn't gain anything?
Yeah. If I just go quickly back to the example, this is an equal operator. You could find rules where you're just comparing based on the similarity and not equals. So you would not be able to optimize. Currently, it just works with the equals operator. So I think it's a very basic stage. So if rules get complex, or sometimes the logical operators here, if there is an OR, we cannot just optimize based on the first operand, right? So in that case, it's challenging, yeah.
Hello, very good. My question is, this is one model to model, like one model to another model, no?
Yeah.
So do you foresee, like, how would be the possibility to do multiple models at the same time? Specifically, for example, that you have a data set of models and you want to have a threshold of this amount of like these models here are similar to this particular one. At the same time, it will be too complex for the the execution time or something like that, or it's not that complex?
Basically, because you can specify a custom matching algorithm, so you can say one rule is comparing model elements from two models, say A and B, and the other matching rule can compare models elements from, say, C and D or C and B. So that's what the language can support. So in ECL, you can support multiple models, but obviously the result would be, how it would perform in terms of execution time is something that we have to see after the experimentation.
Cool. Any last question to Kurat? Yeah.
Okay, thank you for the talk. You briefly mentioned that because of caching, you may have some problems with memory. I couldn't really see the scale for the last plots that you showed, but apparently you had really, really big models. Did you reach, like, what's the estimation you have for the memory that's used for these very big models? And if it's too high, is it actually usable for those very, very large models?
Yeah, it's a good question. Because I think so when we were comparing using the normal ECL, we've reached the point where it was taking like 2 hours to compare two models. So we haven't reached to a level where it was like memory, full memory. But because of the time restriction, we couldn't like go to the higher models to basically compare, because for the normal ECL, it would go timeout. But because it's caching and it depends on how many rules are optimizable, it can reach to that level where, memory cannot take it anymore, yeah.
Okay, so thank you very much, Kurat, for the presentation and the nice answer. I think we can thank again Kurat and give her an applause. And now we are moving on to the last presentation of this session, which is given by Judith from the Aachen University. And she's going to talk about how we can bridge the gap in between heterogeneous modeling and integrated viewpoint modeling. Now he's going to do some magic. Yep, excellent. So the floor is yours, Judith.
Thank you. Yeah, thank you very much for the nice introduction. My name is Judith Michael. I'm a postdoc at the chair for software engineering of Bernhard Rumpe at RWTH Aachen. And it's a great pleasure to present research we are doing together with Malte, Nico, Christian, Florian, and Bernhard about deriving language families, and I'm happy to being able to share our experiences with you in this talk. Now, why should we care about language families at all? If we think about the complexity of the world, we have, for example, energy systems with different entities, technologies, and stakeholders involved. Or if we think about production systems, which is a main area we're caring about in Aachen with our colleagues from mechanical engineering, where you have complex life cycles, materials, processes, and server physical production systems. Or also in the transportation systems, where you have different participants, technologies, or sensory information that you have to handle. You have very complex systems where you have different perspectives and heterogeneous information that you need to handle. And we think that one method to handle this complexity is to use different domain-specific languages. But this requires us that we are integrating the different perspectives that we have, the viewpoints that we have, and also the purposes that different stakeholders might have when they are using these different languages. This leads us to an increasing number of domain-specific languages covering these different domain concepts that we need. And from a research perspective, it's especially interesting that we further analyze how we can foster reuse as one of the good best practices that we have in software engineering to increase the quality and productivity that we have when creating domain-specific languages. The main research question we tried to further elaborate within this paper is how we are able to integrate different modeling languages via different language composition techniques that we apply to achieve such multi-viewpoint modeling languages. And clearly, we use a certain technology space. I will not provide you the full details of the slide, which Nico has already given you in session 2. Just the main aspects which are interesting here from this technology. Montecore enables the fast and easy engineering of domain-specific languages, and it allows for reuse. We especially support different language composition techniques, and it allows us to define modular language fragments. And those are the main functionalities that we are using now within the next slides. For the easy and fast engineering of domain-specific languages, we have established 3 different layers of languages in Montecore. On the base layer, we have different kinds of language components which can be which are reusable, and those can be full or just partial components. And to give you a little bit more insights into this, this feature diagram shows the main set of these language components, where we have basic types, we have basic symbols, expression basics, and the literal basics. I think one of them has even not found a place on this slide because I got it too late. Basically, if you want to have more details about it, you can find the grammars and the details on GitHub and also in some of our publications. The basic principle that we have behind these language components is that we created them to be most reusable in different kinds of languages. So for example, we have here this SE unit types for math and the one for computing. One of them allows us to define, for example, meters per second speed, and the other one meters per second double speed, where we also have this type information. This is something which might be not interesting for physicists if they would use such a language component. So we have here 2 different kinds of components that could be integrated in domain-specific languages. And I'm quite sure this feature diagram will increase in future if we find also additional language components that could be reused also for other projects. On the second layer, we are talking about domain-specific languages, so fully functional domain-specific languages with a specific focus. This could be, for example, different UML languages like class diagrams, object diagrams, state charts, or also other kinds of languages. And on the third layer, we are talking about different language families. We also call them multi-viewpoint languages because they enable us to cover different perspectives of a system. And especially this layer is now where we want to focus on in this talk. So to reach this layer, we want to reuse what is already existing. which is basically both the language components but also complete languages that we already have created. And we still want to be able to maybe add something new or redefine parts of the languages that we have already created or the components. Therefore, we have to rely on established language composition mechanisms to create these larger language families. I will give you a short overview of the 4 different language composition mechanisms we apply here. The first one is inheritance. So here we are using an original language and we are extending the new language as an extension of this existing one. Now, what is interesting about this new DSL is here we can still adapt and extend or modify concepts that we have used, created in this first language. So you have an example here where we have extended the class diagram language. We are using the CD class non-terminal and overwrite it. We change the terminal here from class to entity. Now, if we would create a model from this language, it would has entity, then the brackets, then a list of attributes, and another bracket. This is a non-conservative extension. So it means models that we might have had from this language 1 at the beginning are not valid anymore if we use this new kind of language, which we have composed using language inheritance. The other more conservative kind of language composition is language extension. So here we are creating a new DSL, but the existing elements can only be modified or extending in a non-restrictive way. With this kind, we are making sure that the models of the original language, so the language L1, are still valid when we have this language extension. You have an example here, again, a class diagram language, where we are again overriding the non-terminal CD class and add a new CD method. This CD method enables that we include method signatures into the class bodies of our already existing language, which means we have both models without the method signatures and models with model signatures, which are now valid in this new language. And yeah, you can find other details about that in the paper. The third language composition mechanism we are talking about is language embedding. This is interesting if we want to integrate multiple domain-specific languages, so we have not just one language, we have several of them, and we combine their production rules in a single grammar. You have here as an example where we use the automata language together with the common expressions which we embed in this language. This results in a new grammar for a melee automata, and in line 4 you can see that we are able to import additional artifacts and advance the normal automaton that we had to a melee machine, which enables us to process an import and producing a corresponding response action. The last mechanism, I will not go into it into detail because I think Nico has already talked about language aggregation. So basically here we have still the different artifacts of the languages which can be kept as different artifacts, but we ensure via the symbol table that we have a loose coupling between them and that the different models are able to work together in a whole system of languages. Now, when we're talking about modeling languages, we can't use very simple examples because that's not fun. So we have brought with you 2 larger language families that we have created over several years now in different projects. One of them is the Monty Things language family, which has the aim to simplify the development of IoT applications. We have created an MDE approach for that, for the design, development and analysis of such IoT applications. And the interesting part of it is that it enables lifecycle support, which means you can start at the beginning in an iterative development approach from prototyping to deployment of the whole IoT system until its operation within using a digital twin for monitoring functionality and also supporting maintenance, for example, with error identification during runtime. This was especially developed by Christian, so you can find out more details in a quite long PhD thesis, which is already available, but also some other publications which we had at Modelers Gypsy and in the JSS journal. What is behind that is a language family, which is based on a component connector architecture description language, which we use to generate C++ code for distributed applications, as well as scripts for the container packaging that we're able to deploy the system. We can also supplement the generated code or overwrite it with handwritten extensions, which are basically given by Montecore, and its functionality of the top mechanism. And together with this core functionality and core languages, we have also added other kinds of languages, like for configuring models for hardware or software platforms, defining tests, and other kinds of languages. The second large language family that we have used as a use case is the assist language family. That's basically a large part of my research. So here we have the aim to simplify the development of assistive systems. And if we talk about assistive systems, we aim to provide human behavior support. It could be in different kinds of situations, like for manual assembly and production, to driving, or to activities in daily life. This is not only interesting for old people, because basically when everybody of us is stressed, we're also forgetting some things we should do, or we're forgetting routines. And if you're doing new things in a job, you need training to follow certain processes, so it could be used for different kinds of systems. The idea is to support such assistive systems with using MDE approaches, and we use the MontyGem generator to develop web applications together with a language family, either to generate large parts of this system with a domain model, a language for graphical user interfaces, and also OCL to generate the core part of the application. And we have created two additional languages, the context language to include objects during runtime, and the task language to include processes, and both of them are basically natural language based, so that people without software engineering skills also understand the concrete syntax of these languages. Now let's have a look into the different composition scenarios one could find when we are defining domain-specific languages. The first scenario is based on one domain-specific language. So if we modify a language and tailor it to a specific use case, which means we are creating a new domain-specific language and use another one as a base language, we could apply both inheritance as well as language extension mechanisms. In inheritance, it's interesting for us if we have, for example, no former models that we want to reuse, and it's already clear that we need our new tooling anyways and can't really reuse the tooling that we had before. Extension, here it's more interesting if we are able to reuse tooling and might not need very domain-specific concepts which are not covered in the existing language. The second scenario is when we extend a language to a use case while still maintaining the integrity of the original models. So here clearly language extension is more suitable because this makes us, gives us the possibility to still reuse existing models. Here it is important that the language workbenches that we use ensure that we keep these modifications really conservative, so that they also provide warnings if you're doing other things which you shouldn't do. Now, the first two of them were about using just one domain-specific language. The third scenario here, we are also talking about language components. So the scenario would be to combine different language components into a domain-specific language. Here, suitable method is, for example, embedding. This is effective when the DSLs share common interfaces. It also means that no glue code is necessary, and a prerequisite to do that in a good way is that your DSL developers are aware of the language components which exist, that they know what to reuse in a meaningful manner. What is not suitable in this case is, for example, language aggregation, because it would be just a loose coupling, and you can't use the components into a fully functional DSL without adding additional information. The fourth scenario, here we are talking about already more than one domain-specific language we have to handle. So we want to combine different domain-specific language into a language family. They are already fully functional languages. Here, both embedding and aggregation would be suitable. It really depends on the use case. If we want to have integrated views where for the users of these models, they have embedded information already in one model, not caring about if there are different DSLs behind it, or if you want to keep separate artifacts. The same basically also occurs for scenario 5, where you want to construct huge domain-specific languages with different constituents. Here, the aim is that you support the organization and structuring of larger modeling projects. Again, both embedding and aggregation is possible, but it really depends on the use case, which of these methods is then more interesting for you. The sixth scenario we're looking at is to construct a large language family with heterogeneous parts for interdisciplinary use. This requires that we have interdisciplinary teams which are using the models and modeling language later on. And here the artifacts represents different domain-specific visions on a system. Therefore, aggregation is very suitable in this case because it enables domain experts that they have views in these different kinds of models without getting distracted by information from other perspectives, so you can have very focused information for very specific stakeholders. Partially suitable would also be language embedding. And the last biggest scenario we can have a look at is the modularization of model artifacts, especially if you work with domain-specific languages over a longer amount of time. You'd start to modularize your languages more and more. Here, we do that because we want to have a separation of concern and also create a suitable modeling project structure. For this approach, only aggregation is a suitable composition method. Now, if we look into the bigger two large language families that we have in our paper, you can see already in Monty Thinks that different of these scenarios would apply. Monty Thinks is composed of 46 grammars of the Monty Core project, with reusing more than 4,000 lines of code of these grammars. For example, it reuses the Monty-arc language, which you can see here, but in a non-conservative way. So it is extended, for example, for error handling, but some of the constructs had to be refined. We are extending the statements, for example, and using that in Monty Thinks. We are reusing existing components, like here for the SE units, for example, but also parts of the OCL project. And we have, for example, the class diagram project here, which we use for defining complex data structures. So, for example, so that we import symbols via language aggregation here. You can also see that it was getting a very huge language, so we also had to start to think about modularization here again for Monty Thinks itself, but also for the configuration language, for example. If we look into the other language family, the assist language family, here we have languages to generate the system on the right, and we have the context language and the task language, so they're both with a concrete syntax based on natural language text here in the middle. We have, for example, a conservative extension for these SE units when we found out that it would be interesting if you have, for example, a cooking and recipe support that you need tablespoons and other units which are not existing in the SE unit projects. We are also reusing a lot of the language components which are already provided by Monty Core itself. When we are using these units, They are directly embedded, for example, into the context language. Here we are using language embedding as a method. We can also use concepts of the context language within the task language via language embedding. Again, we have class diagram information as separate information for types, and also this enables us to have different views for different roles. Because basically these parts here are more technically focused, and in the context language we have this more natural language-based view for the users. And we also modularized the language over time into different kinds of language components, so like these article and direction components were taken out of the context language after some time. And you also see that there are some further plans to change the language, for example, that we are reusing the BPMN language and extend it for the different kinds of task types, specific task types that we need here. But this would still enable us to reuse tooling which is already provided by the BPMN language then in the longer run. Now, you have seen it's a lot of different kinds of techniques and methods if you're working in larger language projects. Here you can see an overview of the different scenarios. You can also find them in a paper. And what we have seen is that the more sophisticated the language becomes, the more likely it is that we apply a more elaborated approach. This means methods like inheritance and extension is typically used if we keep the scope within a single domain or a certain use case. And when it comes to embedding or aggregation, those are typically the techniques that we are applying for multi-viewpoint modeling and also for larger language projects. Now, I hope I have shown you a little bit more about how to capture complex systems using different kinds of techniques and how to enable language families by using embedding and aggregation possibilities. You can find more details in the paper, and I'm happy to answer your questions.
Thank you very much, Judith, for the presentation. So, is there any questions in the room? We have plenty of time for the Q&A session.
Thank you for your talk. I was wondering, when defining the feature diagram for language families, one of the most critical parts is that when requirements evolve over time, over the years, you may need to change the feature diagram, and then the language implementation must match the new version of the diagram, so they are always kept aligned. So my question is, did this problem happen during the years working with language families? And if it did, how did you manage it? And maybe if you ever considered doing a bottom-up approach in which the feature diagram is extracted automatically from the language implementation rather than the other way around.
You're referring to the feature diagram for the language components, or?
Yeah.
I think basically we just use that for presentation here on this slide. Yeah.
I think if you can use a mic in that case.
So basically, it was just a graphical representation here for the feature diagrams. So we are not using the feature diagram language to represent language components. They are independent language components, but the feature diagrams shows how they could be used with the different relationships that they have between each other.
So as a follow-up question, then the composition is handled in a programmatic way, not at a model level, right?
Yes, it's done at the grammar level, not at the model level, basically. If you're really doing changes in the grammar itself, you have to also care about model evolution. For that, we also have applied some techniques to identify how the models should be changed and can be changed, but this is something which is up to research right now.
Okay, thank you very much.
There was another question, yeah, Thomas?
Yes, thank you for the presentation. I would suspect that in many cases, the quality of the small language components influences a lot what you can do with them. So basically, it's the problem of how to break down a language. If you start with a big language and you try to break it into different pieces, there is an infinite possibilities to choose the individual components, and depending on how you do it, it will be easy or not to recompose the entire language. So did you ever face the situation on these two language families where you thought that you should use a particular composition operator because this is the one that's the most, that's the best for the scenario that you have, but the components that you have do not match? And they're just really hard to compose together because they were not designed in the proper way.
I would say up to now we did not have the problem that the components did not match together. What is a problem is if the developers are not aware that the components exist and they still develop their own methods then within the grammar itself without reusing a component. But this is something which you have to do then afterwards in a, let's say, stabilizing phase of the grammars itself, so that you have more experienced developers who can give you feedback on that and say, maybe you shouldn't have done it that way, but you should have included the language component which already exists. And it was also, I would say, in last times when we had to change the grammars towards that, quite easy, because you have the integration mechanisms of the language components, and it's quite easy to, get that part out of an existing grammar and take the language component instead in this grammar. So that's, I would say, a very practical approach also for developers. Like, you would lose a library in a programming language, for example.
Okay, thank you.
Any other question? So I can ask mine in the meantime, Judith. So looking at the paper during your presentation, you seem to distinguish composition operators that are based on grammar versus model, which is probably more meta-model than model, by the way. And I was just wondering, what is for you the pro and cons of having composition operator on grammars or versus meta-model? I mean, is there any pro and cons, and what are the benefits of one with regard to the other ones?
Basically not. I think you could also establish that operators also on meta models. Yeah.
No specific.
No specific reason for that.
Okay.
No.
Is there a last question in the audience? No. So it's probably time to conclude. Ah, yeah. Please, Andreas. Go for the last one.
Thank you for the talk, Judith. I'm wondering if we would, or if you would continue this line of work, how would you go on to find new composition scenarios to validate this framework?
I'm not sure if much more composition scenarios exist. If they exist, I think we would also need examples from industry where they have also larger language families. There are some companies out there who have created their own language families, which I know, and I think that could be an approach where we could get additional examples from. Based on the ones I think that we have covered, at least for the academic world, hopefully all scenarios, which might be interesting from different complexity levels. But yeah, so I think we would need other examples from industry for that.
Thank you.
Thank you very much. So this concludes our session. Thank you very much, Judith. I think we can give a big applause to her.
Okay, welcome to the last session of SLE. So this is a session on tools and demonstration. Well, this is a conference on engineering, so we'd like to build tools to make useful things, and we had an invited talk about no code, and this one is about low code. Okay, so please go ahead, Jerome.
I'm Jerome Pfeiffer. I'm from the University of Stuttgart, and I'm happy to present today to you a low-code platform for the systematic component-oriented language composition. First, I will present some motivation and background on the underlying concept, and then afterwards I will tell you about the low-code platform itself and give a short demo, and at the end I will discuss and conclude. So, as we know, domain-specific modeling increases abstractions and thereby also increases productivity. For instance, this article here created web applications using a DSL, and it was less than 20% of the effort than performing the work manually. For us, textual external DSLs require 3 definition artifacts or definition dimensions. First of all, the syntax describing how the models appear. Our concept bases on the syntax definition in grammars. Then we have well-formedness rules that constrain the models of the language, and we have semantics that define what the models mean. So, in contrast to the efficiency of DSLs themselves, their reuse is still complex and inefficient. That's because it requires a lot of white box knowledge. For instance, when combining 2 languages, you have to care about how the syntax, the well-formedness rules, and also the semantics are realized, how they can be combined in detail internally in the respective technological space. And you also have to know how to parameterize the composition operators, and you also have to know what is the result actually when composing 2 languages. Because it is so complex and inefficient, we oftentimes tend to ad hoc develop new DSLs from scratch or don't use DSLs at all. Yes, and to facilitate this reuse, we applied component-based software engineering to software language engineering and encapsulate language constituents into language components. These components have a defined interface and thereby make the internal definition artifacts of the DSL explicit via extensions. We differentiate between provided and required extensions. Provided extensions provide language concepts to other language components to be reused, and required extensions make the need for integrating language concepts explicit. And then we can combine languages by plugging these language component interfaces into another. On top of this language component definition, we also developed a method to systematically compose these components. We have this notion of DSL families that are a product line of languages that where each feature in this product line is realized by a language component, and the features also define how the components are combined. And then someone, a DSL owner, can select features from this language family and derive a language variant. Yes. So from this concept, we designed a low-code platform, and it's an associated language reuse process. So we stay building languages with a language workbench of our choice. In our work, it's Monticore for now, where we still have these 3 dimensions of language definition. then our platform should enable to import existing projects, language projects, and automatically derive a language component notation from it. Then we want to have a library functionality to like browse through existing language families, existing language components. We also want to define new language families, and we want to be able to configure these language families to derive new DSLs. And ultimately, we want to export our composed language and use it, of course. So, the software architecture of this low-code platform is a classical 3-tier software architecture with a front end, which in our case contains 4 UI components. Then we have a back end comprising a controller, which does the user management, data access. And at the heart of the back end, there is our Scholar framework, which is decomposed into 2 software components. One, the language family tool is responsible for processing language family models and guiding the composition process along the feature tree. And then we have the language component tool, which is able to process language component models. And we also have made it extensible to not be restricted on Montecore. And therefore, we have these green components that are extensible with other technological spaces. So basically, the artifact composition might be different in other, or is different in other technological spaces. All right, then let's jump into the demo part. Yes, first we log in, of course. Then we get to the main menu. With the language workbench, no, not the language family workbench to build new language families, and then the 2 libraries for viewing existing language families and components. In the component library can view and also import new language projects. So after importing the project, we can configure its extension points. So in this demo, we want to develop a state chart family. So right now we are importing a basic state chart project, language project. After configuring it, it's available in the library. You can click it and see what's contained in it. Or what its interface looks like. Next, we want to create a new language family. For this, we go into the workbench. Here you can decide whether you want to create a new language family or you want to open an existing one and update it. So we want to create a new one. And in the first steps, you basically build up a feature tree. So we start with the root feature state chart, and then we want to have transitions, right? And we also want to have some kind of guard, and then you can define the connections between the features. To build up the tree. You can use the well-known relationships available in feature models. Yes, and after you created the feature tree, you can connect the features with the language components from the component library and bind the constituents of it. Here we bind the production rules, and we will now jump into the finished language family and configure it. So we select the features by just clicking them, and then we push the button derive DSL. Then we export the project as a zip file. Yes. Yeah, and then we can just unzip it and yeah, have the composed language in our file system. Yeah, here you can see the composed grammar. I think it's a little bit too small. Yes. All right. Limitations for now are that projects have to adhere to a specific structure. They have to be written with the language workbench Monticore. So we are restricted to the syntax definition in Monticore. We are using code generators for the semantic mapping. And also we are restricted to the language embedding and aggregation composition operators and in additive language composition in general. In the future, we want to improve the error reporting and general stability of the platform. We also want to integrate LSP generation to make the composed languages more usable and also make them containerized so that the users who want to start modeling can have a low barrier to do so. We also want to support X-tags and more composition operators, of course, and we also want to perform a user study and evaluate it with further case studies. All right, then let's conclude. We've seen a low-code platform for language composition, which supports the import of language projects from Monticore right now. You can configure the automatically derived language components. You can view them in the libraries, also the language families. You can create new language families, and you can configure them and thereby export language variants. All this requires no setup because it's web-based, and it's also easy deployable because it's containerized app. Yeah, and on the right-hand side, you can scan the QR code to rewatch the screencast. Maybe you can read also then the end part, and you can scan the other QR code to read the paper and get more details. All right, thank you.
So we have time for questions. Yes, please, Eric.
Hi, thanks. I was curious, you said something about error reporting. What kind of things can go wrong in the composition? This is your future work with something about more error reporting or better.
Yeah, I mean, maybe you can derive or you can configure in the language family, you can configure erroneous configurations that are not allowed by definition of the language family itself. So the feature diagram.
Okay, so some components would not work with other components, and that would be something you have to navigate.
Yeah, right, this too, yeah. And also for the import, we don't check the folder structure, it just gives a cryptic error, and we could improve that.
Yeah, I guess I guess what is sort of substantial things that are errors as opposed to implementation level details of things that are just nicer and prettier. But the point I guess I was asking is that some things are meant to work together and some configurations are not.
Yeah.
Yeah, okay.
You have a question? So I have a question because
yeah.
One of our biggest companies in Portugal, OutSystems, developed the low-code platform that is used worldwide, and they are coining this term. And so, have you considered to use that platform to implement this language composition? Because you built it specific for your.
Yes.
text.
No. I built up the app from ground up, so I didn't use a low-code platform to kind of bootstrap this this low-code platform. So no, did not do that.
Okay, so it's picture again.
Yeah.
My presentation is about a tool for definition of the deployment of platform-independent bots in open source project. And Adam is giving the talk. Thank you.
Okay, great. So I'm Ademait, and as Joao said, I'm presenting our tool, which is to define bots for open source software projects that is platform independent. I've made this work with Javier Cánovas de Izquierdo and Jordi Cabot. Okay, so first, we want to introduce the open source concept. So open source is any kind of code that is publicly accessible, so anyone can see, modify, or distribute as they can see fit. These projects are developed on a decentralized and collaborative way, which rely usually on peer review and community production. These projects are usually hosted and developed in social code hosting platforms such as GitHub or GitLab, which provide a set of tools and to create this kind of software in this collaborative way. These platforms are built on top of Git and rely on the so-called pull-based development model, which consists on copying the original repository and submitting a pull request to propose new changes. So, and in this kind of platforms, or in this kind of projects, the workload is usually done by passionate developers, which in theory would be several developers, but this is not usually the case. So the alternative, or some solutions that recent repositories applied, is to apply bots in this kind of projects. The use of bots can be positive, but it has several drawbacks. It involves manual coding and expertise on the platform APIs or offerings, and therefore these bots are platform dependent, making it very time-consuming to create any type of bot for projects that are hosted on several platforms, such as the case of mirror repositories. Furthermore, these automatisms or bots are usually code-centric, and we know that in open source software, the code developers aren't just the world community. There's more social aspects to take into account. So, to the best of our knowledge, there is no DSL to build bots in open source software in a way that is agnostic to the platform that is hosted, the project. And with our approach, the bots are defined independently of the platform, so it access to the platform elements transparently. Our architecture can be depicted as it follows, which it has two main structures, which is the tool infrastructure and the runtime. The tool infrastructure includes the DSL definition, that is the set of syntax to define the bot, and a set of helpers to facilitate the definition of bots transparently. So, the abstract syntax of our language can be clearly organized into main components. The open source software domain sublanguage, which is required to access to the elements of open source software projects, and the bot sublanguage, which are the core language constructs to define the bots. The open source domain sublanguage can be extracted from the open source, or the extraction that we made and we named open source domain meta model, which extracts all the main elements from multiple platforms. We did it just for GitHub or GitLab, which represent all the available tools or features that the platforms offer to open source software projects to construct their software. As we can see, the main element here is the repository present in every code hosting platform. and all the assets of these platforms are hosted inside the repository, such as well-known users, wikis, etc. And this is the starting point when defining a platform, a repository, an open source repository. So, for instance, I won't enter into details, but I'll define some concepts or abstractions that we made. For instance, we detected that the issue sample request can be abstracted as an abstract concept that is contribution, and that is sharing some information, and also has shared elements such as comments or milestones, for instance. And this facilitates the definition of elements in a transparent way. So one abstraction that we did was contribution, and the other one was to distinguish between platform users and Git users, or console version users, that in this case is Git. And we abstracted its instance as a plain user. In this case, we can relate this to users as the joining point is the email, and this is sensitive information, but it was our original thought. On the other side, the bot sublanguage can be extracted from this bot meta model, which we can start by seeing the bot definition, which is the instance of the bot that is listening an event from the platform. This event, for instance, can be the creation of a comment or a push or commit, something. So there can be optionally a condition that the bot has to fulfill to be triggered, to be executed. And some examples of events are the ones that are shown in the zone classes. These are just a few examples, but there are plenty more. For instance, we can see that the contribution comment would be an abstraction of the issue or pull request comment, and this permits that the bot is defined transparently to the specific concept of the platform. All the elements that we've seen before in the other meta model would be the domain elements seen at the right. And this can, we just define this class to as a parent class of any domain element, so the bot can access. And at last, to define the behavior, we propose two initial concepts, two initial instances, which would be executes and creates. The execute instance is proposed as a more complex behavior, and that can interact with the domain elements as it wants. On the other hand, creates is just a behavior, an instance, to create a domain element in response to the event that we defined following its condition. So we designed our DSL as a textual language for the sake of simplicity and understandability. And we decided to implement it as an internal DSL, relying on Java, to also, or at the beginning, escape to Java when we want to execute some more complex behaviors. And we relied on Fluent interfaces using the method chaining pattern. On the right side, there's an example of how would appear our DSL, which follows the Fluent API structure. So the keywords that we defined were 6, in fact, that for instance, the first one has to be declared always at the beginning and is unique and gives the identification of the bot and starts the flow. Right after the creation of the bot, we have to define the condition, the event that is listening, and optionally, the condition that has to fulfill. For instance, in the case that I've shown, would be an event from an issue, and we can optionally say that this issue has to fulfill, has to have some number of comments of some attribute that the issue have to fulfill. So right after the condition, the on statement, we have to define the behavior. This can be a creates or executes keyword, depending on what we are intending to. So the create statement, it creates directly the domain element, and the executes escapes to Java to create more complex systems and interacting with other concepts outside the open source domain meta model. So the example that I've shown before is that one, and as we see, I don't know if it's readable, but we start with the create bot statement. Right after, we go to the on condition, which the first part is the contribution comment, the event that we are listening, for instance, an issue comment or a pull request comment. And the other side, which is a lambda expression written in Java, is the condition that we have to fulfill. In this case, that the issue has to have one comment. And when this statement, the on statement, is fulfilled, we go right after the creates, and in this case, with the use of helpers, create the issue comment with the body of our choice. And at last, we use the validate to fulfill, to mitigate the ending problem in the method chaining partner. So besides the example that I've shown you, that is the first one, we would also like to show a more complex statement example, which would be using the executes statement. In this case, we can, well, the creation and the on statement would be similar. In this case, we are just checking that the pull request has been created without requested reviewers. We can do that thanks to our domain meta model. And the execution, the behavior, is defined with Java. And what it does is to send, well, it doesn't mind, but it sends an email to the maintainers accessing to the concepts that we could extract with the domain meta model. We made this example to highlight the potential that it has to escape to a generic programming language, such as Java, and leveraging on their library and ecosystem. On the other side, we've built the runtime, which we defined it to transparently interact with the platforms, in this case just GitHub and GitLab, and it's composed by the event listener to track the events from the code hosting platforms and trigger the execution of the bot. These events, as we saw before, can be generic or can be more specific. We are trying to do it the more generically possible. And on the other side, the bot uses the connectors to interact with the platforms transparently. So in this case, we could add new platforms in the tool that the only impact that should have is to create more set of connectors. So here we have presented the tool to define and deploy bots in an agnostic way to the platform that is being deployed. We are planning to extend to more platforms such as Hugging Face, Bitbucket, or SourceForge. And this is the first step towards a more vision, to a more ambitious vision towards providing a swarm of bots, which would include the collaboration, cooperation, interaction between these defined bots, and apply other NLP techniques or use a large language model to interact in a more specific or more particular way in each project. So that's all. If you have any question, go ahead.
Questions, please? Yes, Thomas, please go ahead.
Okay, thank you for the presentation. Have you tried to re-implement existing bots that are used by well-known OSS projects, for instance, bots on GitHub that are implemented with Probot, in order to compare the expressivity of your language with what Probot provides for defining bots?
Yes. Thank you. Nice question. We did it in this work. We didn't include it as we were in a initial state. But what we tried to do was to replicate some of the well-known bots in GitHub or GitLab and defining with the DSL, also to compare the required lines of code to express the same behavior, the easiness or the facility that it should have for other developers or external contributors to not knowing generic programming language. And we plan to introduce it in the upcoming work, which would at this phase of validation with existing bots in the platforms.
Thank you. We have time for one more question. Okay, so I'm curious. So you are embedding your DSL in Java, aren't you? Okay, so in embedded DSLs, we have some advantage and disadvantage. So looking at your DSL expressed in Java doesn't look very elegant, let's say. Why don't you, have you considered to put a notation and just have your textual notation for a DSL and let's translate it directly to Java?
Well, not the translation part, but we considered that if we wanted to have the most configurable way of bots, we should have an extensive domain to say. And when we plan to do an external DSL, that is just for the domain that we planned, we saw many inconveniences and restrictions. So we escaped to Java just for the behaviors that go beyond the open source domain. So, for instance, the on statement, we were planning to change it to OCL, sorry, language. So to be more specific, and in the case of execution, I execute, offering more helpers or connectors to facilitate this coding in Java and be more in the context of our domain. But thanks for the view.
So thank you again. Well, and next speaker is Peter Moses, who is talking about navigating in names. Yes, please.
There we go. So good afternoon. I'm Peter Moses, and this will be mainly a demo-focused presentation. My title is a bit too long for comfort and not terribly memorable. A bit too long for comfort and not very memorable. So let me start by trying to simplify the title a bit. Just go away remembering hyperlinked twins, or linked twins if you prefer. You can also visit that website that's shown there. The URL is in the paper as well on the first page, so you don't need to spend time noting it down. Okay, so in the paper, there's an introduction and it explains what name-based code navigation is and what software metalanguages are, and refers to some prior examples of websites that can be thought of as hyperlinked twins. It also discusses technical details of generating hyperlinked twin websites in general using any IDE or language workbench. And it also reports on experience of using SpoofX for that purpose. Has anybody here heard of SpoofX? Okay, that's pretty encouraging, thank you. One of the reviewers, in fact the expert reviewer, was kind enough to comment on the paper that it was blissfully short. Perhaps this demonstration will hopefully, I took it as a compliment, not as an insult, and I hope this demonstration will also be at least reasonably simple and easy to follow. In the demo, I'll be demonstrating, first of all, what it's like to do name-based navigation online in a GitHub repository, in a carefully chosen GitHub repository that doesn't support it very well, of course, and then showing how much better it is to do it locally in SpoofX, and then show what benefit a hyperlinked twin gives you in allowing you to do that same navigation as in SpoofX online in an ordinary web browser without any fuss. And finally, I hope to demonstrate the actual generation process that created the particular hyperlinked website that I'll be showing you. Okay, let me now switch to a browser, if I can do that. This is a GitHub repository. It's not a hyperlinked twin, and in fact, hyperlinked twins are designed not to look like GitHub repositories, so that you won't mistake them for these things. This is a language project that can be downloaded to SpoofX and used in SpoofX, and it has all the source code for that project online in GitHub. Well, let me go straight to show you what it looks like in GitHub, what I would call dead code, and you can just browse it, but if you try to click on symbols, well, you can click on a symbol, but it doesn't do anything. And if we, for instance, browse down and we see something interesting that we like, for instance, this OK single expression, OK, we could type a slash in GitHub, and there is some search facility on the repository. So if we insert our name and a return, then we get some results. And in this case, about 35, no, actually about 40 matches altogether, none of which, at least the first ones you see are not the definition of this symbol, but references to it. If we show more of these matches, then the first definition that we see is actually for a slightly longer word that has an S on the end. We could have avoided that by putting quote marks, I think, around the word when we searched for it. And if we browse down a bit further, then we actually find the definition that we might have been looking for. So there's also another way of that we can search on GitHub. If we go back to that previous page, at the top of the file, you see this little symbol here. It says Open Symbols Panel. That sounds encouraging. Let's do that. Oh, symbol outline not available for this file. Try clicking on the symbol. Well, we already did that. That doesn't do anything. And then we could see which languages are supported. So there's a nice page about navigating code on the GitHub and some, I'll make it a bit bigger here. So there's some really popular languages like C# and Python and Java, of course, JavaScript supported. But the language that we've just been trying to browse in, which is called statics, isn't actually there, and there's no immediate prospect of it coming there in the near future. So my experience anyway, and I don't know about yours, but if you meet an unfamiliar GitHub repository and try to find your way around in the hundreds of files in some unfamiliar language, then it's a pretty painful process, and it can be very frustrating. And this is what's driven me to do this work that I'm going to report on today. So let me go back to the presentation. So that was how it went in GitHub online. Let's see now how it looks in SpoofX locally. And well, let me say first of all that to do this locally, you need three things. You need to download the project from GitHub to have it locally on your computer. You need also to have SpoofX installed locally, which is easy enough. You can download that, and it's just a bundled with Eclipse, so you can have it as an app, at least on a Mac, and it works on other platforms as well. But the third thing that you need to actually be effective in that is you need really some experience with using Eclipse and preferably also SpoofX. If you have that experience, then that's an obvious way to do it, and that's what the developers of SpoofX themselves do, and the other users of SpoofX. They download projects, and they already have SpoofX installed, so it's no bother, and they already have the experience of using Eclipse and SpoofX. But if you're not one of those developers, then you may find it a bit of a learning curve to get efficient with using SpoofX, apart from the download bother. So now let me switch to showing you that same file in how it looks in the SpoofX editor. I'm not going to show you everything here. I see I haven't cleaned it, so maybe I should actually clean it. I don't know why I didn't do that in advance. Sorry about that. It'll just clean that, and then all those little red marks will disappear, and we'll be able to browse things properly. It doesn't take very long, luckily. So let's look at that same file again. And once it's cleaned, then I should be able to click on this symbol. Let me just check what's happening in the console while we're doing that. That was unprofessional, I think, that I should have prepared that in advance. So my project I was cleaning, let's see what happened there. Yeah. So I need to show the actual console window. Oh no, actually it's here. As you see, I'm not a terribly experienced user of SpoofX myself, but it's building, and as soon as that finishes building, then we'll be able to navigate okay. That's the kind of confusion that you can get into when you first start using SpoofX. Almost as if I could demonstrate that deliberately. This language is a fairly complex language involving two meta-languages, SDF3 and statics, and in particular statics does take a little bit of time to build. Just let's finish building, and then I think we're ready to go. These things take a terribly long time when you're actually in a demo and waiting for it to finish. It's not too bad if you're sitting at your own terminal it doesn't seem to usually take that long, but we'll, otherwise I'll go to the next stage of the demo, which is already prepared and cleaned. Yeah, there we go. This is now finally about to finish. So what I'll do is just show that at least when we have this cleaned, and the reason it didn't navigate before was that I hadn't been patient enough and given it time to finish building. But now it has finished building, and now when I go to that, you see that all these symbols are actually links, and I can simply click on that, and it will take me straight to the definition of that symbol, and the same for all the other symbols that you have there, and you can click around to your heart's content. So sorry for the delay with that. As I say, if you have SpoofX and experience and everything installed and downloaded, then and you get these things cleaned and built properly, then no problem. But the idea of a hyperlinked twin is to avoid all that hassle. So let's go back to an ordinary browser now, and there is actually, for that same language specification, which is not my language specification, it's somebody else's that I just found on the internet. It's at that location. You can browse it yourselves if you want. It's a significant language. It's been used and developed for other purposes. If we now go and look in this hyperlinked twin, we can just, for instance, click on the names that occur in the imports here and go straight to the corresponding file, and we can browse through that, and we can find the relevant line that we were thinking of having this OK single expression. Click on that, and again, we go straight to the definition. So if you like name-based navigation, if you don't like drilling down through hierarchies of files, then you can browse around and click around on your hyperlinked twin in the same way that you can do it in SpoofX. And the idea is that by generating a hyperlinked twin, using SpoofX from the internal information in SpoofX, you'll get exactly the same navigation in the hyperlinked twin with name-based navigation as you have in SpoofX. You don't need to check it afterwards. It's automatically done. I could show some more examples of hyperlinked twins, but let me now go and to the next bit of the final bit of the talk, which is to talk about generation of these hyperlinked twins. There's a description essentially in the paper that I won't go through in detail here that is telling you the steps that you need to do, essentially generating some HTML and inserting some things in it to get those hyperlinks there. It's pretty straightforward stuff. And in principle, I claim that you could do that using any IDE or language workbench, and other people might like to do it. But I've been using SpoofX to do it. So let me just try and visualize the generation process. So on GitHub, we have a repo with a language specification or some other code. We need to make a local clone. This is for the generation process, not for browsing the hyperlinked twin. This is for generating it in the first place. So we use Git to make a local clone. And then this is where SpoofX comes in. We inject into the a clone of the repo or a fork if you need to publish a fork. Insert the sources for the generated web pages. For every code file in a supported language, you insert actually a markdown file that is mostly just HTML. You can also preview it locally before you publish it. You can use make docs serve to just serve a local preview and browse that to your heart's content and check that it looks okay. And once you've done that, you can just push the changes in the source files, or actually the new source files here. You just push them to GitHub, sorry, at least if you're using GitHub, then there's a continuous integration action that will then deploy that published website to GitHub pages. In fact, the one we were looking at is on GitHub pages. And that's all pretty automatic. So the only thing you need to do in SpoofX is after you've imported and cleaned that language project is you need to choose a menu option. So let me demonstrate that now before I go to the concluding slide. And I need to switch to the development version of SpoofX, where I have been careful to clean the project in advance. And for this statics file, I need to choose a menu item which is evocatively called generate website. And so, yeah, you can see that it's going on down here. It takes a little bit of time, but it is doing a fair amount of name analysis, and well, it's done some name analysis, but it's using that name analysis quite heavily during the generation process. Each of these lines is for generating a particular source of a web page that we can then afterwards push to GitHub, or we can preview it just using, for instance, when this finishes, which is it's just about to finish, then I'll just show you the terminal command that just brings up a preview, and there we are. That was the generation process for that hyperlinked twin. So it's not like something that lasts half a day. It's rather straightforward. And then to preview it, you just type make.serve, and then it'll also pretty quickly serve a local copy of that hyperlinked website. You can do that before you push it to GitHub, just to check. And as I say, well, let's just check that local website is there. This was when the server had been stopped. So yeah, there it is. So we could browse that, and everything will be there. I'll just show you the syntax while we're here as well. That again, you have all these names. So that was the demonstration. Let me just go back to the presentation, and so the conclusion is that if you get interested in SpoofX and you specify or define your language, whether it's a DSL or a programming language or a meta language, using SpoofX, that means defining its syntax, its name binding analysis, and also some highlighting, otherwise you won't get the colors. Then you can generate hyperlinked twins using SpoofX. At least when the demonstrated code that I used in the demo has actually been incorporated and reviewed and included in the release of SpoofX. So yeah, thank you for your attention.
We have time for questions, please. Yes, please, Eric.
Thanks, Peter. So if I'm not a SpoofX user and I have some other system for designing languages and want to do the same thing, so like in Silver, right, we generate some kind of information like this for a language server protocol for going to declarations and stuff. What would be involved in sort of stepping into this process some way along and saying, well, I don't have SpoofX, I have something else, but I also want to generate a bunch of web pages?
Well,
is there a convenient place for that, or is it just a?
I would suspect the easiest route is assuming that your language workbench has facilities for browsing, for traversing and transforming analyzed abstract syntax trees into strings, which it probably does, right?
Suppose, yeah.
Then you could take a look at the rather small amount of Stratego code that actually implements this in SpoofX and implement in whatever favorite scripting language you have for doing it in your own and generate your own websites. The alternative would be to be starting to specify your meta languages in SpoofX and transport the whole generation process into SpoofX. But I don't know, it could be interesting to look at defining the meta language you use in your language workbench as a SpoofX language, and then you get this for free, basically.
It's very cool. Thank you.
Yes, please.
Have you considered exposing the ability to users of the object language to define their own custom notions of name binding? I know the Linux kernel has a similar system called Elixir, and there are several like operating system specific notions of name binding they have across modules to facilitate its own internal module structure and browsing that.
Sorry, didn't quite catch it. The
Oh.
trouble is the loudspeakers are pointing in your direction and not in mine.
Sorry. Have you considered allowing users of the object language to specify their own notions of name binding, in addition to the normal, like, you can look up a variable?
Yeah, I mean, the meta-language statics that's used nowadays in Spoofax was developed by Ilko Visser, who unfortunately is no longer with us. And I mean, he loved, by the way, always to demonstrate Spoofax, and he did it far better than I do. I mean, he wouldn't make that mistake with not having cleaned a project. So it's a very general language, and you can specify all kinds of name binding for different languages. There are maybe some theoretical limitations concerning polymorphism and things like that, but whatever object language you want to deal with, then it would be interesting if you think it's difficult to specify it in this statics language.
Right. I mean, like, it's like internal to the object language. Like, for the case of the Linux kernel, their object language is C, but
Yeah.
beneath that, within the system they're building, they have their own sort of notion of names. They're just strings.
Yeah.
It's possible to extract that statically, but have you considered, like, giving the users power to do so?
Yeah. I'm just not familiar with that context, so I really can't answer that in detail.
Okay.
Sorry.
By the way, when I think on Spoofax, name binding, name analysis, I always think in this wonderful paper of Wilco on scopes as types. Is that related to your work? Are you using it in some way, that technique?
I'm just exploiting the statics meta-language, which is also based on scope graphs, which is closely inspired and related by scopes as types. One of the co-authors of scopes as types is down there and could probably answer that better than I can.
Great work.
But it's basically this is a very simple thing that I've done. It hasn't required me writing any grammars or name analysis. I'm simply taking what's there and using the Stratego API that gives me access to the parse trees and the analyzed syntax trees and the name binding analysis, and then I can just traverse that in Stratego, and it's really pretty straightforward. It's only a few hundred lines of Stratego code at the most, so it's in a sense building on top of all that work that people have done with meta languages like statics and scopes as types, but it didn't require me to have any knowledge of the details of that.
So, thank you for the talk. Making the code accessible in this manner is, well, very useful. I was wondering if you had also considered the integration with the documentation, and maybe if I'm not familiar with how Spoofax does this, but is there some documentation system that also generates a website that would integrate well with your approach?
Yes. Thank you for the question. Yes, documentation is very important, and also I think literate programming, where you have an interleaving of informal text with snippets of formal specification. And in fact, in previous work in a project called CBS, I've demonstrated how to support that kind of language that combines informal explanation with the formal notation. But regarding existing documentation frameworks, like JavaDoc or something like that, then I haven't investigated that at all. But I don't think there's anything built into Spoofax that would automatically do that. But it's a very general toolkit, and lots of ththings are possible in Spoofax.
Thank you very much, Peter. Giving our very last talk in the technical program. By the way, just after this talk, we'll have the closing session, so don't run away. And so this last talk is about practical runtime instrumentation of software language, the case of Skyuk. Is that the way to say it?
Sayuk.
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 Okay.
Yeah. Just checking. Okay. Okay, so thank you for the introduction. I'm happy to present this joint work with Benoît Combal from the University of Rennes and Benoît Lelandais and Marie-Pierre Oudot, my colleagues from CEA. So in this talk, I will present SciHook, which is a tool we designed in a specific context, but with an approach that we believe can be generalized to other contexts. So this specific context is NabLab. So NabLab is a DSL for numerical analysis, which is developed at CEA. And with this DSL, you can define so your variables, which are physical quantities that you want to simulate. And so we can see that you can define the data types are more mathematical in their nature. And so we have simple data types, but also vector and matrices. And we can also attach these variables to mesh entities, which are the discretization of the space in your simulation. So it's really a physics simulation-oriented DSL. Once you have defined some variables, you can define jobs, which are computation units, which will iterate over the mesh to update some variables. So in this case, we are solving the heat equation. So we are updating the temperature at each iteration of the simulation. And then NabLab is also data flow oriented. So we can here see the execution graph of all the jobs that is synthesized by the language infrastructure, which means that language users do not have to specify in which order their computation will happen. The language just analyzes the variables that are read and written to, and it generates the actual control flow graph of the application. So this is on the front side of the language. And then on the back end, we generate several applications for several backends. Mainly, so all of them are in C++. And we can generate sequential applications or multi-threaded applications or multi-process application using MPI. Or then we also can target a framework, the Arcan framework, which is a framework for HPC code, an open source framework we use at CEA, but it's also used elsewhere. And one problem that arises is that how do we debug the code that is generated? Because here, the language user of NabLab, they wrote code like this, but then they have to debug code, which is complex code, complex generated C++ code, which addresses a lot of system level concerns and not numerical level concerns. So because of this, we started this project a while ago, which was to provide a debugger for NabLab. And what we did not want for this debugger is to expect that the user start GDB to debug their generated C++ code, where they have to deal with pointers, reference threads, and so on. So this is not what we wanted to do. We wanted to be able to debug the numerical scheme as it was written by the users, which manipulates vectors, matrices, and meshing entities as their first-class citizens. But not only that, but we also wanted to provide a debugging approach that is suitable for scientific computing, because simulation codes are particular pieces of software. Since they can iterate for over 1 million times on the same single line of code. And this makes breakpoint and step-by-step interactive debugging quite unsuited for this kind of codes. And one of the strategy which is more often than we would like used, which is called printf debugging, can be quite tedious because you can just print the value of a variable. You want to do statistical analysis over your arrays, your variables, and so on. And so just printing a trace requires a custom-made C++ logging library that handles complex computation, so it's also a tedious task. So before we proposed an approach, we took a step back and looked at the bigger picture of scientific computing and development in scientific computing. And what we noticed is that it happens in quite a polyglot way, where the mainly used languages are Python, C++, and Fortran, where each language has its own kind of niche, Fortran being the niche of legacy code, mostly, C++ being the most used language, and Python being the most used language for after the simulation to post-process, to create visualization, to analyze the results, and so on. And also lately for doing AI stuff. And this leads to de facto polyglot development. But this polyglot development happens in the sequential process where we run a complete simulation and then we change the language that is used to use Python instead and analyze the results. So we thought, why not integrate those languages, meaning C++ and Python? We did not look at Fortran, but in the context of a simulation code. And I should even say in the context of a single simulation. So we investigate a language level approach to make these polyglot practices of post-processing, basically, viable for debugging, and by enabling the interoperability between C++ and Python. So what we envision for our approach is to define a language-level behavioral interface, which is dedicated to instrumentation. So we can call it an instrumentation interface. And with this behavioral interface, this instrumentation interface, we identify all the execution events in a language, so all the language constructs that give rise to execution events that allow interoperability with another language on consistent execution states, so states where the state of the memory is legal to access, basically. And this interface also identifies these consistent execution states, so we can expose them to the other language. So with this language level interface, we can, for any program of the language, derive the program level instrumentation interface, which does declare and derives these execution events and corresponding execution states. And finally, we have an instrumentation runtime, which acts as a bridge between the two language runtimes. So we instantiated this approach with Sci-Hook, specifically on NabLab in the first time. And so this here is an overview of how Sci-Hook works and how it instantiates this approach. So here on the left, upper left, we have the specification of the simulation code, which is typically, in our case, written in NabLab. And from this specification, we can generate the complete simulation code. Note that we also have a case, I won't expand on it, where the specification is not complete, it's only architectural, and it only generates the skeleton of the complete application, not the actual behavior, but we are still able to generate the instrumentation interface from there. So, yeah, so since we define our language level instrumentation interface, we are able to derive all the execution events and corresponding execution contexts for each program that we generate. And this instrumentation interface here interacts with the Sci-Hook library to declare the execution events. and to emit them during the execution. So then what the user can do is write instrumentation scripts in Python, which they register for the execution, and they will be run. How to say? The Scyhook library will be able to execute those scripts when the events, the execution events, are raised by the simulation code. And so these, to do this, the library interacts with the CPython interpreter to be able to actually run the scripts. And the user has access to all the scientific computing libraries that they are used to be using for analyzing the results of their simulation. So here is an example, an excerpt of an instrumentation, a generated instrumentation interface for a C++ application generated with NabLab. So the actual application code is here. And so here we can see that we have a loop that will update this UN+1 variable on each cell of the domain. And what we will do is that before this loop, so right at the beginning of this job called update U for updating the temperature, we will instantiate a context for this of the application to be exposed to Python. And then we will emit the corresponding events before and after the execution. And so this context is declared generated as well, extending the Scyhook execution context. And it will expose the memory basically as NumPy arrays so that they can be manipulated with the NumPy library. And this is a view on the memory. There is no copy happening, which allows the language user to directly interact with the NumPy library efficiently. And yeah, and here I didn't talk about it, but this is the registering of the events that we are raising here, which happens at the beginning of the simulation. So what can we use Scyhook for? So here we are, this is an instrumentation script, which is Python, which imports the Scyhook library, and also the instrumentation interface, which is exposed in Python, to be able to register instruments, what we call instruments, which are Python functions that will execute on the raised events. So here, this function will load a reference solution, which is stored as a JSON file, and will compute the difference between the temperature at the current state of the simulation and the reference solution. And we will then compute the max error over the complete domain, and if this error is superior to 10, which is an arbitrary value, we will trigger a Python breakpoint, which will allow us to enter into interactive debugging to run some more Python commands to try to understand what is going wrong, or to just kill the simulation because it has no meaning anymore. So this is an illustration of how to use Scyhook for debugging, but we quickly realized that it's relevant beyond just debugging. So we are basically in this case here, we were envisioning this case mostly, where we debug the simulation code, but then we realized that it can also be applied when we are trying to validate physics simulation code with regard to experiments, and most importantly, for when language user needs to define a custom model, like custom physics parameter, like rainfalls or the temperature over the boundary of the domain, or such things. Or they also need to pre-process their data and to initialize their simulated domain to with some agility. And here, Sayuk is also quite useful because you can do this in Python instead of using filling XML files and so on. So here is a quick example of how it can be used. So here we are using Sayuk to implement a lightweight simulation workflow where we have a first instrument that will initialize the temperature over the domain. Then we have a second instrument that at each iteration will constrain the temperature over the boundary of the domain to be 0. And then at the end of the simulation, we will display a heat map of the result of the simulation. And something I've not mentioned is that this allows to have results, to visualize a result without doing any I/O operations, which are the thing that take up a really big chunk of the execution of a simulation. So it really allows to iterate quickly to calibrate a simulation. And so speaking about that, here is some performance evaluation where we can see we have two baselines. So here we have a baseline without IOs, where we are not writing any data. So basically the simulation is useless, but it's still computing stuff. And here we are writing the data. And so just to be quick, the monitoring case I showed you is here. And so it shows that by only monitoring and not outputting any data, we can still validate some properties and be faster than if we did dump all the data. And the lightweight simulation is really a huge speed up because of not having to do any IOs. So to summarize, we designed Sayuk, which is a tool and an approach to debug simulation codes. And we leverage the existing polyglot practices to make them viable for debugging. The tool relies on a language level approach to generate the necessary instrumentation, which exposes execution events where a dynamic instrumentation can happen and exposes a domain-relevant view of the corresponding application state. And we found the approach to be relevant beyond debugging, and that when instrumentation scripts can replace the original IOs of the application, we can obtain great speed up. So for our future works, we envision additional integration, like being able to instrument directly C++ code with source-to-source transformation. So this is a work in progress. We also envision to integrate directly at the LLVM IR level, and maybe propose a Mojo implementation of Sayuk if this language takes off. We would also like to be able to JIT compile our Python script, for example, with Numba, which is a rising library in this respect. And here are a few features we could add to the library. So thank you for your attention.
Time for one quick question, please. Okay, so we are looking for the closing session. So I have a question. So when I think about source code instrumentation, I always think something was very popular 20 years ago, aspect-oriented programming. Couldn't you use a system that could instrument the code for you that is part of the motivation for that community?
What do you mean? I'm not sure.
So normally when you want to instrument your code,
yeah.
Okay, you can do it by polluting the source code with implementation code,
yeah.
Or you can have define it in a kind of an aspect that is later weaved to your code. Couldn't you use?
So here, since we are generating the code anyway, this is the polluted code is code that is never touched by the users. So it's less polluted in a sense. But this is also the reason why we want to investigate LLVM to instrument directly at the LLVM level, yeah, to have a more clean approach and to integrate with more languages than just C++.
Thank you. So I think we thank the speaker again. Yeah, and we are just on time to start.
Ah, great. Yeah, I'll be very brief. This is the closing of this SLE 2023. So many thanks. First of all, to our organizing committee, to Joao, and to the PC chairs, Thomas and Elizabeth, and to our publicity chair, who is not here today, but luckily he agreed to serve as a publicity chair probably forever. And of course to all of you, the attendees. So important to make this a viable thing. So thank you very much. There will be a next edition. And it will most probably be in the US, in Pasadena, which is a part of LA, if I'm correct, and co-located with SPLASH'. That will probably be announced tomorrow or in the coming days. And we jumped ahead and have already assigned the PC chairs. And we, the steering committee, consider ourselves very lucky to have this sort of extraordinary couple. A mixture between gender, of course, between continents, and if I may say so, Peter, also ages. And I'm really thrilled by this composition and looking forward. I think you already started thinking about PC, and so we are a bit earlier this year than we've been last year, which turned out to be a bit of a problem. As I already said, our eternal publicity chair has also been assigned. We still don't have a general chair. Just to remind you of the variety that this conference offers, we have research papers, we have new ideas and vision papers, and we have this comparatively new category, which is perhaps little known, body of knowledge papers. It's not entirely clear what makes a good body of knowledge paper. It's apparently not necessarily something new. Something that should be sort of adopted, accepted, general knowledge in the field. It's not a literature survey, but it's something sort of in between. I mean, you can try out. I really want to encourage everyone who has something sort of acquired some knowledge and you think that this is really stable and settled to try and write a body of knowledge paper about this. And then, of course, the tool papers. And that was it. I hope to see you next year, and I hope to see your friends next year and your students, and so let the conference thrive. Thank you.